Alright, you guys, so number one for this paper 2 is a pretty intense trigonometry problem. And so before we even get into parts A, B, C, whatever, okay, we first need to really understand the tools we have in the world of trigonometry. And there's three main tools that you will embark upon. So for trigonometry, I really need all of us, because once we understand this, the rest of the exercise will flow very smoothly. We all need to understand the main three tools for trigonometry. The first one, which the one that I suggest the most, is a sine rule. Okay, I immediately need you to associate or write down in your notebook or paper that sine rule works in pairs. Then you have cosine rule. And cosine rule, I need you to write down somewhere in your pen or pencil or paper or whatever that you use cosine rule if sine rule doesn't work. I'm not even kidding, okay? And last but not least, the third one that it's common to forget, honestly, is that you do have a way to calculate area of triangles using trigonometry, and this you will use if you don't have height. Now, why do you use the trigonometry formula for area of triangles if you don't have height? Because what we're used to doing, okay, if we look at our formula booklet, is if we look for area of a triangle, the classic is the one up here. Base times height divided by 2. Base times height divided by 2. You've probably done this like 100 times. See? Well, the other formula for area of a triangle, bada bim, bada boom, here it is. So look at that. You can find the area of a triangle without the height. Over here, you need the base and the height. Down here, what you actually need are two sides and one angle. Now, you might be looking at this and asking yourself, how the heck do you know these are two sides and one angle? And that is why I need to explain the formulas just a little bit. See? So the first thing I also need us to really understand and hone down and like really hone into, focus into, is the following diagram, okay? In your triangle, okay? Let's say we call this side A. So if this side is little a, then its respective angle is going to be big A. And I can also go backwards. I mean, if this angle here is big B, then the little side associated to it is going to be little b. So, look at that. Lo and behold, you can also figure out that if this is big C, then this side over there has to be little c. Okay, so that's the first observation I will like sort of point out, is that small letters in the context of these formulas are going to be sides, while big letters are going to be angles. So big letters for angles, small letters for sides. And so technically, if you look over here, that's why this guy online was telling me that sine rule works in pairs. Because if you look at the sine rule that's up here, okay, if you look at the sine rule that's up here, we'll take a good look. First of all, you have two equal signs, okay? So technically, you can use it like this, like little a divided by sine of big A equals little c divided by sine big C. Or you can use it like this, comparing only A with B. Or you can use it like this. Okay, so that's the first observation I'm going to talk about. It works in pairs. You use whichever pairs you want. So for example, coming back over here, my sine rule, we said, right, is that you compare technically two sides with two angles. See? Now the more intuitive version of this, right, if I were to to get rid of the letters and put maybe words into it, is that technically all you need is side 1 divided by sine of angle 1, so its corresponding angle, the side with the corresponding angle, equaling some other side divided by sine of the angle in respects to that other side. See? So technically from here, if you have 3 out of 4, let's say you have side 1 and angle 1, and you have side 2, this is good enough for you to find angle 2. Okay, so as long as you have 3 out of 4, you can find the last one. That is why I tell you to think in pairs. The moment that you have a single pair, a single side with a single angle, then you can probably find some other missing side that you don't have the angle of, and using the sine rule, you'll figure it out. So the moment you have a single pair, sine rule is probably something you can use. Okay, that's what I'm trying to tell you. That is the blah blah I will give you for sine rule. Got it? For cosine rule, we're only going to use it if sine rule doesn't work. See? And I know this equation might look kind of nasty, but the only observations that you really have to do is that you have 2 formulas for cosine rule. See? You do have a semicolon here, so that means that you can pick between either. And really, they ask for the same thing. Okay? The only observation that I'm going to draw from here is that one of them has a side alone, while the other one has an angle alone. Okay? The other thing I'm going to mention is that it does matter which angle you're leaving alone or which side you're leaving alone. Because notice, in this context, whatever you call A or whatever you call B is simply going to add each other. It's simply going to multiply each other. And that is the scenario in both cases. So if you switch up A with B or B with A, nothing's going to change in your procedure. A plus B is the same as B plus A. A times B is the same as B times A. So switching up A and B doesn't matter, but switching up C here really does. Because you only have cosine C, so you really have to be careful. The side that you're trying to find, whatever angle you put inside has to be its corresponding one, okay? Or also over here you have minus C, okay? If you confuse sorry. If you confuse A with B, it doesn't matter here. But if you confuse C with B, well, one of them now has a negative, the other one has a positive. That's going to change a lot to your approach. See? So that is the small observation I would do here. Notice which one you're having alone, okay? And work from there. See? Anyways, cosine rule, you're only going to use it if sine rule doesn't work. See? So I'm not going to get too into it. Let's just see it in action later. And last but not least, the area of a triangle for me is very visually appealing. See? So again, following the same idea that instead of talking about A, B, C, and all that stuff, I'm going to call them side 1, angle 1, side 2, angle 2. In this context, if I were to put this in a little more friendly way, I would say that the area of a triangle, you can calculate it as 1/2 times side 1 times side 2 times sine of angle 3. And so notice, this, for me, I can explain it more in a visual aspect. See? So whichever sides you end up picking, the angle that you put into this formula has to have nothing to do with those sides. Notice you have side 1 times side 2 times sine angle 3. So this angle has to not be associated to either of the sides. From a more visual aspect, you can find the area of a triangle. For example, I'm going to draw 3 of the same triangle. See? And I'm going to give you the 3 scenarios where you can use this formula for area of a triangle. See? So the first scenario, following the colors as well, you can have side 1, you can have side 2, and the angle that is in between. And notice this angle that is in between is associated to this side here, which clearly has nothing to do with side 1 and side 2. So this is a scenario where you can use, or you can find, the area of a triangle. Got it? The other scenario following that idea would be maybe this side and this side. And so the remaining side is going to be this guy here. So the corresponding angle, of course, has to be this guy there. Oh, look at that. So basically, at least for me, from a visual aspect, it's a lot more friendly. Basically, if you have two sides and the angle in between them, you can find the area of the triangle. Yes, it is that simple. Yes, we will have to use it. See? So these are the three scenarios for area of triangle. You now know all the tools you have to know. Write this down somewhere. Get familiar with them, because once you understand it, this exercise over here will turn out to be very easy. Dale? So let's jump into the action now that we understand these formulas a little bit better. From here we have that the diagram shows points in a park viewed from above at a specific moment in time. We have that the distance between two trees at points A and B, so this is tree 1, this is tree 2, is 6.36 meters. One small observation: anytime they give something of information of your diagram, make sure that it's there. So this 6.36 is right here. Okay, so all good in that sense. Make sure your diagram has the information that they give you. If not, put it in yourself. Odette is playing football in the park and is standing at point O. So at point O, we have our good old friend Odette. Such that AOB is 10 degrees, which is already written into my diagram, so I'm going to check it. Then they tell us that OA is 25.9, all right, and that OAB is obtuse. So this distance is already written here, so that's cool. And when they tell us that OAB is obtuse, let's remember, you can have acute angles, you can have right angle angles, sorry. So this is in the context for angles, okay? You can have acute angles, you can have right angles, or you can have obtuse angles. All you really have to know is that for acute, it's any angle that is less than 90. Right angles are angles that are equal to 90. And obtuse angles are angles that are greater than 90. And so from here, it's pretty clear that it's going to be an angle that is bigger than 90, but nonetheless, it might be relevant later on. So OAB, which is basically telling you the angle formed between O and B. So between O and B, clearly you have angle OAB at A, basically. You know that that angle is obtuse. See? So for part A, we need to calculate the size of ABO. ABO. So if we need to find this angle here, well, what did this guy online tell you? First of all, you should probably not trust guys online, but at least in terms of math, you can trust me, okay? That being said, for calculating the size of ABO, this guy online told you initially you have three main tools, and you're going to start off with sine rule. See? If sine rule doesn't work, then go to cosine rule. ¿Vale? So your procedure will always be try sine rule. If it doesn't work, go to cosine rule. I know there are other ways to solve this faster. I know you've probably heard of SOHCAHTOA, but to be honest, I'd rather give you tools that always work. So an approach that will always work is try sine rule. If it doesn't work, go to cosine rule. Okay? So I know there are quicker ways, but my procedure that I'm going to show you today is like the conservative way, what's always going to work. You might take a little bit to get there, but you will get the answer. See? So this guy online told you first try sine rule. He also told you that for sine rule, it works in pairs. So do you have a pair here? We'll take a closer look. Technically, this angle here is associated to that side there. So check, I have at least one pair. And the angle that you're trying to find over here, which we will call X, has associated to, boom, that side here. And you actually have that side. So look at that. You have side 1 and angle 1 right here. Side 1 is 6.36, angle 1 is 10. And then you have the side 2 right here of 25.9, and you don't have the angle of that 25.9. So sine rule here actually works perfectly. So let's first write down the equation. So A divided by sine of A equals B divided by sine big B, right? So the other thing I'm gonna just put a disclaimer here in case you're not so familiar with it. Remember, small letter is the side, while big letter is the angle. If you have trouble remembering that, take a good look at the formula. Sine big A is for angle, see? And so whenever you have sine, cosine, and tangent as a function, you always put an angle inside. You never put a distance, see? So that's another way you can remember it. What's inside the sine, cosine, and tan? Angles. And so if a big letter is inside of sine, then big letter must be angle. All right. In this context, I know it says A and B and stuff like that, but you define A, you define B, you define what is side 1, angle 1, you define what is side 2, angle 2, okay? I know that the letters can be confusing, but the more intuitive part is what should remain for you. Be consistent. First angle with first side, second side with second angle, okay? It doesn't matter if this point is called A or this point is called B. You define it however you want. Dale? So what I'm going to define it as is I'm going to say that these guys in green will be my first pair. See? So if these guys in green are my first pair, that means I have 6.36 divided by sine of 10 degrees equaling, and now it's the part in black, cierto? So my my side for that angle X is going to be 25.9 divided by sine of X. And from here, you just need to get X alone. The procedure will always be the same. You will be technically, you will cross multiply here. So from here, you do this times this equaling this times this in an attempt to get X alone. So if you go ahead and do that, which helps you get rid of the fractions, by the way, you end up with sine X times 6.36 equals 25.9 divided by sine of 10. From here, in order to keep getting X alone, clearly you have to divide by 6.36 so that, you get X further alone, right? So that goes away with this. So you end up with sine of X equals 25.9 divided by sine 10 times 6.36. And from here, the interesting thing you have to do is that X, in order to keep getting it alone, it's within a parentheses. And so if it's within a parentheses, you need to get rid of whatever is right outside. And what's right outside, sort of, right? I know that technically no, but what's right outside is the sine function. So how do you get rid of the sine function? Well, just a little bit of context. If you were solving an entirely different problem, like 2y equals 4, and I tell you to solve this, well, what do? Of course, you're going to tell me you divide by 2. Okay, but why do you divide by 2? You divide by 2 because this 2 to the y is multiplying. And what is the inverse function of multiplication? Division. So that's why you divided both sides by 2. So whatever is affecting your variable, you do the inverse in order to get it alone. If it's being multiplied, you will divide. If it's being, added to, you will subtract. And if you have a sign, you have to do inverse sine. Look at that. So if you do inverse sine from here, well, you got to do it to both sides, right? It's the same as like simply dividing or multiplying by 2, just that in this case, it's going to be sine inverse. So if you do it to both sides, the magic that happens is that this goes away with this, and you end up with only X. So X will equal sine inverse of that whole thing, okay? Before I plug it into my calculator, it is very important that in mode, you have it in degrees, okay? The common is to have it in radian, as I just did just now. Make sure that in mode, you change it to degrees, because this does change how your sine behaves. So sine 45 in degrees is this, while sine 45 in radians is actually going to be this, okay? Small detail, I'm not going to get into why, just for us at AISL, focus on leaving it on degrees every single time. Got it? So now that we have it in degrees, we can go ahead and plug in sine inverse of that whole thing. Sine inverse is on top of sine, okay? So you do second sine to hit sine inverse. We're putting a fraction here, so I'm going to put alpha y equals and press the first one just to plug in a fraction more easily. So I'm going to go ahead and solve it from here. 25.9 divided by sine of 10 times 6.36. Close parentheses, keep it nice and clean. error in domain. All right, I probably wrote something wrong somewhere here. So sine inverse of 25.9 divided by this, da da da. Why would sine 10 be wrong? Da, da, da. Let me check my work. I'll leave it in the video because this is relevant for the approach. Boom, boom. Boom, boom. Okay. Cross multiply. Okay, yeah. So, I'm leaving it in the video because everyone makes mistakes and this could happen to you as well. Whenever you have a domain error, the first thing you should check is, okay, is something in my, did I plug in something wrong? Now I double checked and nothing was plugged in wrong, but it did have a pretty massive mistake, which is right when it cross multiplied. See, right when it cross multiplied right here, what should have happened, right? I did have sine x times 6.36, so that's good right there, but I should have also done 25.9 times that sine 10. And I divided it immediately, and I don't know why. All right, so that's my bad. Technically, from here, I should have that 25.9 times the sine 10 times the other guy. See? So this is divided by 1. Yeah, there it is, right? And so from here, this sine 10 is actually on top. So 6.36 times sine 10. All right, usually I would edit it out, like do the problem again and stuff like that, but I'd rather keep it real, you know? This is math. Everyone makes mistakes. Even this guy on YouTube, even this random guy on the internet, everyone does mistakes, okay? The important thing in life in general is what do you do after those mistakes, see? So check your work, learn how to improve. Learning how to think is the most important thing, see? Not knowing what to think, instead learning how to think. And a big part of that is correcting yourself in the appropriate way. So I checked my work. That was the mistake that I had. I go back over here. I'm going to clear probably everything. There we go. So now it should work. See, so 25.9 times sine of 10 divided by this guy here, 6.36. There we go, there's my answer. It's basically 45 degrees. Let me show you the mark scheme so that you guys actually trust me for what is the remainder of the video. There it is, yeah, 45 degrees. Notice how you get literally a method point just for trying the sine rule, see? So, in this context for part A, for angle ABO, so part A, we will have 45 degrees. See, you could just leave it as 45 to be honest, okay? So that is for part A. Later on for part B, it asks us to calculate the area of triangle AOB. And so the triangle that you have right now, if I were to redraw it, see, so this is for part B. Technically, the triangle that you have right now is that over here you have 10 degrees. Yeah. Over here, you just found that this is 45 degrees. And you know that this side here is 25.9. And that this side over here is 6.36. Yeah. Now, for area of a triangle. For area of a triangle, I mentioned way earlier that you will use the formula for calculating the area of a triangle if you don't have the height. And in this context, the height of this triangle is actually pretty hard to come across. See, you would have to like do even more trigonometry to try to find the height of this triangle. See, so that's a little bit harder. And so because we don't have the height, we're going to be using the trig formula for area of triangle. Now the trig formula for area of triangle, as I mentioned earlier, is that you need two sides and the angle that's in between. You need two sides and the angle that's in between. So in this context, well, the two sides that you have are right here, right? So following the color coding, you have these two sides right there, and you need the angle that is in between. Technically, I could try to find the other side down there and use one of the other angles, but I think it makes a lot more sense if I work upon the sides I already have and try to find this angle here. Now for this angle here, it's fairly straightforward. The degrees inside of a the degrees inside of a triangle add up to 180. So 180 degrees, adding up all the different angles, has to equal, well, my missing one, which we will put it as just green. So the missing one in green, yeah, missing one in green, plus 45 degrees, plus 10 degrees. And so 180 degrees has to equal what we have in green, plus 55 degrees. Okay, so in this context, you're going to end up with the angle in green being 180 minus 55, 125. So this angle in green is 125. That means I can now officially use the formula for area of a triangle, which is right here. So area of triangle, whoops, is 1/2 times AB times sine C, which, as we mentioned earlier, is really just two sides and the angle in the middle. So side number 1, I will call it the 25.9. Side number 2, I will call it as a 6.36. And the angle in between is obviously going to be sine of 125. So all of this into your calculator. Trust the process always. If there's one thing that's cool about the AB is that the process and the methodology is very repetitive. So once you learn it a couple times, trust the process, trust yourself, trust the hours of study you've put into this. Put it all into your calculator, take it a minute, and there you go. So the area of this triangle has to be 67.467. 67.467. We are talking about meters. This is all in meters, so this is going to be meters squared. Okay. If you wanted to do significant figures, you count 1, 2, 3, round it up or keep it the same. You round it up. So in significant figures, you can leave it as 67.5 meters squared. So that is for part B. We check our answer just to keep things clean, and there it is. Okay. So notice once again, all you really had to do was notice that you need to use the area of a triangle formula. Okay. So once you realize that, you're good to go. This angle right here, well, because I use sig figs or whatever, you can leave it as 125. It also works. Okay. No worries there. That was just the decimals thing. See? In other words, in case anyone is freaking out in respect to the answer key, if you did it using this number, you would get that number. ¿Vale? And you would get this. But if you round it just a little bit, which is completely legal, this would end up as 125. Here you would plug in 125. You end up with 67.5, which is exactly what happened over here using significant figures. Okay? So no worries there. Everything is good so far. Then it gets kind of wild, right? Because they tell us that Odette's friend Khemil is standing at point K such that he is 12 meters from A, and also for some reason we know that angle KAB, which is this angle here effectively, is 45 degrees. So everything in my diagram is, still there, nothing new or nothing hidden to discover. And so for part C, we need to calculate Khemil's distance from B. So all you're really working with is this triangle here, okay? Yes, they're putting a bigger diagram because they're adding onto the context of the previous triangle, right? Because the previous triangle is right here. So they're adding on to that previous sort of context. But really, all you need for part C is this triangle here. So yes, you actually don't need parts A or B for what happens now. So you have this triangle here. You have one of the sides. You have the other side. And you have the angle in between them. And so for calculating Khemil's distance from B, you need this last sort of side. So what do you have? Okay. Well, this guy online told you, always try to use the sine rule, and if you can't, go to cosine rule. So from here, do you have a set of pairs? Well, this side is associated with this angle, so there's no pair there. This side is associated to that angle, and so there is no pair there. And this side is associated to that angle, so there isn't a complete pair there either. Now this guy online told you, yo, if sine rule doesn't work, go to cosine rule. See? So I go to cosine rule. For part C, we need to calculate a distance. Right? So if we're calculating a distance in cosine rule, as I mentioned earlier, one of these, the one on the left, if you take a closer look, has a side that is alone, while the one on the right has an angle that is alone, okay? And when I say alone, it's like C squared, little c squared equals, right? So it's isolated by the equals. That is what I mean by it is alone, okay? Here you have a cosine C equals, and so the angle is alone in that sense. So let's go ahead and write down the formula over here. The formula is little c squared equals a squared plus b squared minus, I think, yes, minus 2ab cosine c. And so all we really have to do, quick recap from before, is that whatever side is alone, you need to have its corresponding angle. So wow, look at that, how convenient. And yes, it is that convenient in the IB. When the sine rule doesn't work, you usually end up using the cosine rule, and you have just what you need for the cosine rule. ¿Vale? So the methodology that you apply is absolutely essential. Trust me on this. Sine rule didn't work, you go to cosine rule, they're asking for a distance, so use the cosine rule on the left side, and you go ahead and just fill it in. You just fill it in and forget about it. See? So the big idea here is that this side here, C, which we're going to call this side here in red, ¿cierto? Has associated to this angle right there that is also in red, right? So as long as you're consistent with that and have the other two sides, you're good to go. Which you do. We're going to call A this light green side over there, and we're going to call B this light blue side over here. So if you go ahead and plug in from here, clearly you end up with C squared equals 6.36 squared plus 12 squared minus 2 times 6.36 times 12 times cosine of the angle in red. See, so 45. Got it? From here, just to keep things clean, I guess, since we are talking about the distance of Khemil from B, so it's from K to B, this is the distance KB. Yeah? And so just to keep things clean, I'm going to put KB over here so that we all understand what's happening here. See? I'm going to put a little bit of a line on top to show that we're talking about a line, we're talking about a distance. Okay? Yeah. So KB squared, in order to get rid of the squared, you have to do square root to both sides. Because if you do square root to both sides, this goes away with this. And that means that you have square root of this whole thing right here. See? So in other words, for getting KB, I think I might have gone a little bit faster. So let me go again. See? So in this context, we're talking about the side KB. Got it? Now, following the formula, you have C squared. And so in order to get rid of the squared, you just gotta do square root. So if I square root everything onto both sides, this goes away with this, and you end up with KB alone. So KB equals the square root of the entire thing on the right side. So KB has to equal the square root of the entire thing on the right side, which will be 6.36 squared. So that's this guy here, ¿cierto? Plus 12 squared. Whoops. Minus 2 times 6.36 times 12 times cosine of 45. Make sure it's all within the square root. You press enter. There it is. So Khemil's distance from B, in other words, the distance from K to B, has to equal, or it equals, better said, 8.747. All right, and if you were thinking in terms of significant figures, you count 1, 2, 3, round it up or keep it the same, you round it up. So in significant figures, if you'd like, you can leave it as 8.75. Right? We are talking about 3 points here, so keep in mind the units. It's all in meters. So meters. Just so you believe me, here it is, 8.75 meters. So again, you just have to realize you have to use the cosine rule. Now, a lot of people ask me, how do you realize you have to use the cosine rule? And it's not that I realize I have to use the cosine rule because no one knows the formula by heart, but you do have a procedure associated. So try the sine rule. If it doesn't work, you will use the cosine rule. Like I can bet my life on it, okay? Especially for AISL, that is the procedure that you gotta follow, okay? Keep it in mind, trust me on it, at least for this one. See? Yeah. So that is for part C. Then it gets kind of wild with the last two parts. See, for part D and E. They tell us that XY is a semicircular path in the park with center A, such that KAY is 45 degrees, which is written right here. Khemil is standing on the path, right? And so Khemil, which is at K, is on this path right there. And so the path, or in other words, this half circle, point K is on it, okay? And they tell us that Odette's football, this is important for later on, Odette's football is at point X. So right here at point X, we will have the football, okay? Then they tell us that length KX is 22.2. So this right here, which I'm putting in green, is 22.2, okay? KOX, so another thing that is actually not on my diagram, so KOX, so angle O with the sides K and X, so KOX, if you were to put some lines over there, this angle, see, is 53.8. And what I will be putting in pink, angle OKX, so OKX, so OKX, so this angle here has to be 51.1. Alright, so now I made sure that everything was in my diagram. It usually is, but notice for part D it wasn't. That is, so always check the information that they give you. Make sure it's in your diagram so that you can visualize it all a little bit better. So for part D, we need to find whether Odette or Khemil is closer to the football. So let's recall. From part B, we know that Khemil, or for part C better, we know that Khemil is standing at point K. So at point K, we have our good old friend Khemil. While from way earlier, they told us that Odette is playing football, blah, 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 and is standing at point O. So Odette right here, or better said, Odette is right here, okay? So of these two people, who is closer to the football? The other way to understand it is point O or is point K closer to X? Okay, so really what I'm dealing with is this triangle that just got created between red, pink, and green. So let's redraw it so that it's a little bit easier to handle. So right now, you know that this is 53.8 as an angle, ¿cierto? You know that this is 51.1 as an angle. You know that this side is 22.2. You know that here you have Khemil, here you have Odette, and here is X for football. X for football, I don't know why, but okay. So this is what you know about your triangle, right? So all you really have to do now is, you know the distance Khemil has to the football, it's 22.2. From K to X, it's 22.2. Now all you have to do is find the distance from O to X. Compare both and see what happens. So, trigonometry. Again, same procedure. First try to use sine rule. If not, go to cosine rule. So, sine rule works in pairs. Do you have a pair here? This angle goes with that side. You have a pair. And this angle goes to that side, which is actually the side that you're trying to find. You're trying to find OX. So wow, look at that, sine rule works. More than that, the procedure works. First do sine rule, then do cosine rule. Trust me, it'll be okay. Dale? So again, the formula is A divided by sine big A equals B divided by sine big B. So in this context, the first pair, I will use the one in pink. So the first pair is 22.2 divided by sine of 53.8, equaling the distance you're trying to find, which is OX, right? So the distance OX divided by distance OX divided by sine of 51.1. And so now we make sure to not do the same mistake from before. If you want to get OX alone from here, because it's at the top, you can actually just multiply by sine 51.1 to both sides. Why would you do this in the first place? You do this because then this goes away with this, and you end up with OX as a distance being alone. Okay? So that is what you can plug into your calculator. That helps you find the distance of OX, which will be well, obviously I have the fraction, right? So you have the fraction 22.2 times sine 51.1 up top, which is what's in red, divided by sine 53.8. Here I didn't really put the point very specifically. I have a 53.8. ¿Vale? Yeah, go ahead and press enter. There it is. Distance OX is 21.4099. Okay? So, just so that we're on the same page, there is the 21.4099. Okay? And as I was mentioning earlier, now that you filled in this triangle over here, 21.4099, now you have to compare who is closer. And basically, which number is bigger, the 22.2 or the 21.4099? Clearly, the bigger number is 22. All right? Don't fall into the trap of the 4099, which sounds kind of big, right? Like 4,099. It's after the decimal. See? It's after the decimal. So clearly, 22.2 is bigger than 21. 22 is bigger than 21. So if 22 is bigger than that 21, right? Then that means that kx, distance kx, is bigger than distance OX. And so if kx is bigger than distance OX, then Khemil is farther. And that being said, Odette is closer. It's very important that you do this mini sort of conclusion near the end. See? Never forget what they're asking for. They're asking for you to find who is closer to the football. So it's not enough to do the trigonometry and this fancy math. You also have to conclude. That's also why it's worth 4 points. If you look at the mark scheme, you literally have a whole point that is you figuring out who is further from the ball. See? So careful with that, especially when it's worth a lot of points. There's probably 1 or 2 extra things you got to do. ¿Vale? So that is for part D. And last but not least, part E is a little bit different. So we have that Khemil runs along the semicircular path to pick up the football and to calculate the distance that Khemil runs. And so this is a little bit harder, right? So let me erase the diagram for a second, because now we're not really talking about trigonometry anymore. Now we're talking about a circle. So oof, now it got a little bit harder, see? So let me erase this diagram. Let me clarify exactly what they're asking for and exactly the tools that we can use. So first of all, it's not trigonometry anymore, because trigonometry is for triangles. It's for triangles. This isn't a triangle anymore. See? So we have that our good old friend Khemil is running along the path in order to reach the football. And we need to see how much the distance in pink is. Now, what do you know? Well, you know a couple of things. Dale? You know that when you're talking about circles, you have 2 main tools. Okay? Your 2 main tools for circles are in the formula booklet, which is actually right below to what we were looking at. On the one hand, you have length of an arc and area of a sector. So when you have a circle, okay, this can often get like split up into pizza pies, pizza pieces, whatever you want. See? So if you cut it up like this, the language that we're using here, okay, is that this in red, this in red is your sector. So for area of sector, right? While this in green will be your arc. Ah, okay. And so in this context, you also have a circle. I mean, you actually have, because they talk about a semicircular path, so we are talking about circles. So the 2 main formulas are for length of an arc and area of a sector. So this is for circles, okay? Both of these are for circles. Now, in this context, because we're talking about the distance that Odette that Khemil is going to run, we will probably end up using the one for length of an arc. Area of sector, probably not, but let's keep it in mind. It's there, it does exist. Yeah. Now for using either of these, all you really need is the angle for your arc, right? So if this arc in green, that means you need this angle there. And same for the sector. I mean, if you're going for this sector and putting in red, then you need this angle here. You need the same angle, okay? It's whatever. Here's the thing. For the length of an arc, you need the sides that compose that arc. And for area of sector, you need the sides that compose that sector. I mean, the angle in between those lines, whatever, etc. See? Fair is fair, makes sense. Yeah. Enough talking, let's get into it. So, from here, do you have the length of this sector? See? On the one hand, you know that it's a semicircular path. And so this 12 right here, well, what is it? Well, if you were to complete the circle, right, this 12 also shows up here. It also shows up there. It also shows up here. And so this 12, you guys, it does take a little bit of creativity to really see the circle, really see the semicircular circle. But from here, the two main hints are the following. You know it's a semicircular path, okay? And they also tell you, okay, that Khemil is standing on the path, right? So this K is on the path. And so if this is 12, right, and the semicircular path has a center A, then from A to K, you're going from the center of the circle to the edge of the circle. Center of circle, edge of circle, 12 is your radius. This 12 is a radius. So, that's the first big observation you have to go for. The second big observation you have to go for is that the length that is in pink, well, what is the angle associated to? It's the two sides associated to it earlier, right? So this guy in green, I need these two sides in order to understand which angle I need to get, right? And so this arc in pink, I need to understand that we're talking about from here to here. And so we're talking about from here to here, that I need this angle there, okay? That's the big next sort of question you have to ask yourself. See, which angle do I need? Because your formula does depend on an angle. That is, so the formula for length of arc, you have L equals your angle, theta, ¿cierto? Divided by 360 times 2 pi r. So all you need is to figure out your angle and figure out your radius. I already figured out my radius, and for figuring out the angle, because I'm going for the part of the arc that's in pink, then I need to understand that, okay, so this arc finishes here, and it also finishes here. So boom, boom, the angle you need is this guy right there, okay? Yeah, how the heck do you find that guy right there? Well, I can immediately tell you, with a little bit of quick maths and a little bit of magic, that it's 135 degrees. Now, how the heck did this guy online just do that? He just did that because you need to know that a straight line has 180 degrees. That's also why if you have a straight line and you put a vertical line through it, you have 290 degrees right here. Because 90 plus 90 gives you that 180. And the other thing that can help you understand is that if you were to do a circle from here, well, you have another 180. And 180 plus 180 gives you that 360. Bada bing, bada boom. So this is kind of like common math knowledge that you do need to know. Okay, a straight line adds up to 180. And so if this is 45, that means I can do 180 minus 45 in order to get this guy right here. And so 180 minus 45, just so that we all agree, although I'm pretty sure about my math, but let's be honest, anyone in a test puts everything into your calculator, even if it's 2 plus 2. So there it is, 135 degrees. Dale? So here's the 135 I need for my theta, okay, which again, I did explain it intuitively, but the formula here literally says that theta is the angle measured in degrees, right? That makes up your arc, while r is the radius. So I already found theta, already found radius. It's all in degrees. Everyone's happy. All I have to do is plug into this formula right here, which ends up as length equals 135 divided by 360 times 2 times pi times r, which you said was 12. So all of that into my calculator. I like to use the fraction thing because it's easier to plug in. To each their own, whatever floats their boat. 135 divided by 360, that's this part here, times 2 times pi, which is going to be right under clear. So you press second, then this little arrow thing, hit the pi button, times 12. All of that, you press enter, bada bing, bada boom. The distance that Khemil runs has to be, for part E, following this formula right there, 28.27433. If you like significant figures, you can count 1, 2, 3. Do you round it up or keep it the same? You round it up. Make sure you put your units. We are talking about meters all along this exercise. I show you the answer so that you believe me. There it is. All right. You can leave your answer in terms of pi. I don't like to. Okay. To each their own. So you can leave it in significant figures, the entire number, or in terms of pi right there. See, with the 9 pi. When I say in terms of pi, basically what they're doing, just so that you know, is that they don't multiply by pi. See, they leave pi right outside. And so that is how they reach 9 pi. Dale? All right, you guys. For me at least, and this is a closing remark. For me at least, there's two main things I can observe here, right? This is a trig problem. And trig problems are not that hard once you understand the formulas. See? So understand these 3 formulas, understand that you're going to be using them a lot, and understand that A, B, and C doesn't matter. What matters is how you define them. Okay? Be consistent. Little a has to go with big A. Little b has to go with big B. It doesn't matter that your exercise had the letters A, B, and C, and O, and whatever in between them. What matters is how you define the pairs, how you define what goes with what. That it? So don't get confused by that. Do the sine rule first, then do the cosine rule, and more often than not, you do end up calculating the area of triangles when you don't have the height using the trig formula, which is not that hard. For me, from a visual aspect, you can notice more quickly when you have to use it. All you need is the 2 angles and, all you need is 2 sides and the angle that is in between, okay? And the last part, which was like a circle thing, right? Lo and behold, it's paper 2. Paper 2, what it does is that it mixes different units together. See, I know that problem 1 technically is like geometry / trigonometry, okay? But for us, it's like it's mixing trigonometry with length of arc and sector and stuff like that. See? So the catch about paper 2 is that it has problems with like that mixes stuff. See? Even if we look just quickly at, for example, I don't know, maybe number 4, right? Here we're talking about probability, then we talk about variance, then down here we talk about a p-value. So it's not just probability, it's also like doing like t-tests and stuff like that. So the thing about paper 2 is that it sort of has like 2 exercises in one. See? Why is it worth mentioning it out loud? Because even in this exercise, I bet that you can skip from A to D and you can do only E to H because it's literally 2 exercises in one. Okay? That's the cool thing about paper 2. You can claw for points almost anywhere. Even in this exercise just now, you could pretty much do almost all the parts by itself. See? I think A and B were very associated, but like C and D, you can do them by yourself. E as well. Like, I mean, you know what I mean? Like, paper 2, the catch it has is that it mixes a lot of exercises in one, and that can work in your favor. ¿Vale? So keep it in mind. That is number 1 for paper 2. A very thorough explanation, but I think it's a very worthwhile one. See, a lot of the context was understanding the formulas. Once you do that, you will be just fine. Ladies and gentlemen, I hope it helped. That is for number 1. All right, you nerds. First things first, there's a little bit of machinery outside of my room, so you might hear it, a low rumbling. Okay, that's all. Now let's jump into the exercise. Now the exercise, before we're even talking about part A, part B, part C, part D, part E, part F, we will first establish that this is a sequences problem. And ladies and gentlemen, I need you to understand the following. When you face a sequences problem, there are two main types of sequences that you can face. One of them is what we will call the arithmetic sequence, arithmetic, and the other one is the one that we will call the geometric. Now, for the arithmetic, I need you to associate it to adding and subtracting, while for the geometric, I need you to associate it to the multiplying with dividing, okay? For arithmetic, we talk about a common difference. So however much you add or subtract by will be D, while for geometric, we have a common, what we call ratio. So you multiply or divide by a so-called R. Okay, so that's the first thing we need to talk about. An arithmetic sequence is adding or subtracting. A geometric sequence is multiplying or dividing. If you still have no idea what I'm talking about, well, first of all, pay a little bit more attention in class. And second of all, an example of an arithmetic could be maybe something like, I don't know, you go from 2 to 4 to 6 to 8. And so here, clearly, you are doing plus 2, plus 2, plus 2. And just to talk a little bit about the sort of language and vocabulary that can show up for this exercise, this first one is what we will call U1. U1 as in like the first term, okay? This guy, the 4, is going to be U2. This guy is going to be U3. This guy is going to be U4. Because in your arithmetic sequence, this is your first number that shows up in your pattern, right? So this is U1, this is U2, this is U3, this is U4. You can think about it as this is my first number, my second number, my third number, my fourth number. By how much are you increasing? By plus 2 each time. So up here, you would have a D equals of 2. An example of a geometric sequence, as I said, it's multiplying or dividing. So maybe you start with the same U1, okay, you also start with 2, and you also end up with 4, but here you end up with 8, you end up with 16, and so immediately you say, this can't be just adding, because if it was adding, here you have a plus 2, but here you have a plus 4. And so the important thing about the arithmetic sequences is that you always add or subtract by the same common difference, okay? If you have a common difference that is changing over time, then you're probably dealing with a geometric sequence, which would actually make more sense, because if over here you have times 2 instead of plus 2, it makes more sense. 2 times 2, 4. 4 times 2, 8. 8 times 2, 16. And so the common ratio here would be R equals 2. And once again, this would be my first term. This would be my second term. This would be my third term, and this would be my fourth term, okay? So that is pretty much all we need to know, at least from an intuitive standpoint, of what sequences actually are. So after that relatively short introduction, I'd say, now we can jump into number 2. Number 2 for paper 2, we have that Dinah makes pendulums to sell at a market. That is actually really cool. She plans to make 10 pendulums when on the first day, and on each subsequent day, make 6 more than she did the day before. So she will be making 6 more than what she did the day before. And so for part A, we need to calculate the number of pendulums she would make on the 12th day. So the first thing we need to identify is that, this is clearly a sequences problem, because you have an initial amount, then you have, like, the first day she has 10, and then the next couple days she has more and more and more. So immediately you should be thinking sequences. Now the next challenge is identifying, is it an arithmetic sequence or is it a geometric sequence? And as this guy online told you, not that you should trust guys online, but at least this guy for math, you definitely can. Okay. It's an arithmetic sequence, because here it says that Dinah will make 6 more than the day before. It doesn't mean, it's not saying she will make 30% more or that she will double it or triple it. No, it's saying she will always do simply 6 more. And so here you can immediately say, okay, so D has to equal 6. And on the first day, she's making 10. So my first number, my U1, has to be 10. Okay, that is all I know right now. And for part A, you need to calculate the number of pendulums she would make on the 12th day. And so here what they're asking for, technically, by asking the 12th day thing, they're not asking for the total like it shows up later. They're asking simply how many she made on the 12th day. So they're asking only for U12. That is what they're trying to find. Okay, so this is the context. You have U1 equals 10. You have D equals 6. And they're asking for U12. So how the heck do you do that? Well, you could write it out until you reach U12, but that's not particularly exciting. So go ahead, open up your formula booklet, and let's have fun with what they call math. And yes, that's ironic. So over here in the formula booklet, it's very important that you get familiar with it. See? I talk about this all the time in my videos, and the main message is the following. It's no use to have the formula booklet if you don't know what's in it. Because the day of the test, the moment you recognize this is a sequences problem, you should be thinking in your brain immediately, sequences, I know I have a couple formulas in the formula booklet. You don't know them by memory, you're not sure exactly what they do, but you should know that they're in there. And so you read sequences, you recognize that it's sequences, and boom, you're opening up the formula booklet, boom, you're going to the sequences, and here they are. And here, if you studied enough with the formula booklet with you while you do homework, while you do tests at school, because it should be allowed, in my opinion. I mean, you use the formula booklet the day of the AB test, so why not during every other test, right? And so get familiar with it, use it, learn it, love it. Once you get familiar with it, you will start recognizing, okay, so for sequences, I have 2 boxes, right? The box on top is for the arithmetic sequence, while the box on the bottom is for the geometric sequence. And as you can see, they both have like the same sort of type of formula. The one up top is for the nth term, while the one on the bottom for both is going to be the sum of n terms. Okay, so basically one of them is for the sum, the other one is for a specific term that you're looking for, right? And over here, you are looking for a specific term. You're only looking for term U12. And so, okay, so in the formula booklet, I know right now from the exercise, yeah, we'll do it over here, it's fine. So I know from the exercise from part A that U1 is 10, that D is 6, and that I'm trying to find U15 it was? U12, sorry. U12. That's what I'm trying to find, right? And so because I'm looking for the nth term, I need to be using the formula up top, of course. That's going to be my first option. If that doesn't work, we probably need to get creative using something else. But right now, it works if you just go to your first option. So your first option, using the formula up top for the nth term. And as you can see, what does it ask for? Well, look at that, how convenient. It asks for U1, which you have. It asks for N, which you technically have, and I'll explain in a moment how. And you have D from right here. So how the heck do you have UN on the one hand, and how the heck do you have N? This is the thing about having the formula booklet and being familiar with it, because that right there, understanding that you do have UN, is really simply understanding the formula, see? So don't fall into the trap of, oh, I have the formula booklet, so like I'm good to go. No. You gotta know how it works. You gotta know the formulas behind it. You gotta figure out these sort of nitty-bitty details, okay? Point is, because you're looking for U12, technically in this formula, you would be plugging U12 right here. I mean, we can all agree with that. So if you go ahead and plug in U12 right here, u1 plus parentheses n minus 1 times d. Well, notice this n that I'm putting now in red is the same n that's right there. It's literally the same n. And so if you put u12 on this end, you are immediately establishing that you're looking or using the formula with an n equals 12. So boom, you erase this. Boom, you put a 12. Boom, you plug in u1. Boom, you plug in d. And voila. There is your formula for u12. And so the main message, and this is something that will show up all along this exercise, is that you define what n is. Okay, the nth term, you define n. And wherever you define n, you gotta change it all over. Okay, and this will happen on all my equations. This n here will be that n there, that n here, this one, this one, this one. Okay, it's very important that you're consistent with, okay, whatever your n is, it's gonna be your n all over the place. A lot of people get confused and leave un as un. No, you establish n. If you're looking for u12, immediately that should be telling you that your n will be 12 for the formula. Okay, so establish that, understand it, and you're gonna be good to go. Yapo, so u12 is this whole thing. So clearly I gotta do 10 plus 12 minus 1, 11 times 6. So u12 has to be 10 plus 66. And with some quick maths, u12 for part A has to be 76. Just so that you all believe me and trust this guy on the internet, at least for math, here you have that 76 right there. Method point for using the appropriate formula. Cool. Yeah, so part A, let me just put it over here. So for part A, we have that u12 ended up being 76. Let me put it in blue just so that we remember that this is the answer. Then they tell us that she plans to make pendulums for a total. This is such an important buzzword that they even put it in bold. A total of 15 days in preparation for going to the market. And so for part B, of course, we need to calculate the total, once again, the total number of pendulums she would have available at the market. In other words, Dinah will make pendulums for 15 days in a row. And they're asking for the total amount of pendulums she creates at the end of those 15 days. And so, a lot of you might already be thinking, well, I can write out the U1, U2, U3, U4 until U15, add them all up, and I'm good to go. And I'd say, yes, you can do that, but it's a massive waste of time. And this is why you gotta be familiar with the formula booklet, because as I mentioned earlier, focus on what I have in pink. Both for arithmetic and for geometric, you have formulas for the sum of n terms. And so if in this context for part B, we're looking for the sum of the total pendulums after 15 days, clearly I gotta be using the formulas down here. All right, and here goes another important disclaimer that I have to go over. All right, so let me raise a little bit of this to make some more space. This is the following disclaimer. In the formula booklet, oftentimes you're going to encounter that for the sum of, for example, this formula, see? For the sum of n terms of an arithmetic sequence, technically you have two. You have the one over here, and you have the one over there. So what the heck? What's happening? Even for geometric, you have the one over here, and you have the one over there. All right, what's happening here? Why do they do that? Well, for arithmetic, what you need to remember, and not by heart, not by memory, but you do have to remember or open the formula booklet and recognize, there's two formulas. Something was happening here. See? I really need you to focus on the following. When this happens to you in any formula in the formula booklet, okay, really establish piece by piece this first formula. What does it ask for? So this first formula, you need n, for example. You need u1. you need D. While the second formula, what does it ask for? You need N as well. You need U1 and you need UN. And so they have some stuff that is pretty much in common, the N and the U1, clearly. But the main difference between both formulas is that one of them asks for D and the other one asks for UN. And so that's the kind of stuff that you need to be aware of using the formula booklet so that it doesn't get overwhelming, so that you don't get confused. Get familiar with the formula booklet. That's my main message that I'm going to give you in every single one of my videos, because it is absolutely important and essential for you to do well in this exam. So you have these two formulas. Clearly, you got to use one or the other. See? Now, before jumping back to the exercise, let's first talk about the two formulas down at the bottom. If you do the same sort of, I don't know, I don't want to say procedure, but the same approach, yeah? If you do the same approach over here, what does this first formula ask for? It asks for U1, it asks for R, it asks for N. And the one on the right is also asking for U1, is also asking for R, is also asking for N. So this one down here is a little bit more troll. They're literally asking for the same three things. So you really can use either one of them and both of them work. Okay? For the sum of n terms of a geometric sequence, it does not matter which equation you use. I'm not sure why they put 2. Whatever. They both work. Okay, that's what I need you to understand. They both work because they both use the same amount of variables. So there will never be a scenario where you use one over the other. That's what I'm trying to tell you. While up here for arithmetic, there are scenarios where you use one over the other, because the main difference is having D or having UN. And so over here, if we come back to reality for part B, well, what do you have, right? We do have U1 from earlier. We do have D, and we're looking for the sum of 15 days. And so technically, for using the equation on the right, I would need to have U15, which I do not have. I could find it out using this formula here, but that sounds like extra work. And who likes to do extra work? Mostly nobody. See? So from here, instead of using the formula on the right, which asks for UN, I'll use the formula on the left, which only asks for D, which I do already have. Okay? So, lo and behold, for part B, we will be using the equation on the left. So for the equation on the left, I'm going to put S of 15. So immediately putting S of 15 here, let's recall that I'm saying that N is 15. So you're plugging in 15 for all of these guys in red. ¿Vale? So that's the other thing. You are already saying that N equals 15 in this context. So N is 15. U1, you have it from earlier, it's 10. And D is 6 from earlier as well. ¿Vale? So plugging in these three things into the formula on the left, you have S of 15 equals 15 divided by 2 times 2 times U1. U1 we said was 10. Plus parentheses 15 minus 1, close parentheses, times D. D is 6. Yeah, so if you follow the procedure a little bit, you can actually just plug all of this into your calculator, to be honest. Yeah, why don't we just plug it all into our calculator? Talking about doing less extra work. So this fraction here, we can do alpha y equals, press the first one to do a fraction, so 15 divided by 2. Be consistent with your parentheses. Here you have 2 times 10. Another parentheses, sorry, plus the other parentheses, which is 15 minus 1. Close times 6. And then close, close. See? All right, I think it looks the same as what I plugged in over there. I press enter. Error with the syntax. Okay. I know why this is happening. See, and I'm glad this showed up on my video because it's probably happening to more than one of you. So what's happening here is that I put an extra parentheses there. Actually, no, I missed. Did I miss? Oh yeah, I put an extra parentheses here at the end. Now we're okay, ¿cierto? Now we have a bunch of pairs of parentheses. Before I had an odd number of parentheses. Now I can press enter. Now it works. So S of 15 has to be 780. So that means after 15 days, Dinah has created 780 pendulums. That is a lot of work. See, there's the 780 method point for using the arithmetic sequences sum formula. All right, cool. So that's for part B. So for part B, we can write that S of 15 ended up being 780. Let me put it in blue so that we recall that this was the answer. We keep on reading and we have that Dinah would like to have, important, at least 1,000 pendulums available to sell at the market and therefore decides to increase her production. She still plans to make 10 pendulums on the first day. So we still have, what this is telling you is that you still have that U1 is 10. But on each subsequent day, she will make X more than what she did the day before. So instead of making 6 more, now you have a new D. So D, well, it says X more, so D equals X. See, so D is something that you don't have anymore, okay? And so for part C, we have that given that she will still make pendulums for a total of 15 days, so it's still for a total of 15 days. Calculate the minimum integer value of X required for her to reach her target. So there's a couple of things happening here. And this is where you have to have a greater understanding of the formulas, see? So on the one hand, we're still making a sum formula because we're still talking about the total amount she wants for 15 days. Now, here you might be working a little bit backwards because as I mentioned earlier, technically the difference between these two formulas is that one of them has D, the other one has UN. But also, if you get really creative with it, and sometimes working backwards, ¿cierto? Sometimes instead of plugging X and getting a Y, you gotta plug in a Y and get an X. And for these formulas, the same thing is happening, ¿cierto? Technically, the other thing you can be plugging in here is literally S of n. And yes, it's something that they both share because they're both, like sum formulas. But technically, there is a scenario where you plug in S of n, you plug in n, u1, and etc., and that helps you find D. So let's see how that happens. So, and how I figured that out, right? So it's very important that you highlight these buzzwords and go figuring out which formulas which variables you have and which ones you don't in order to see which formula you use. Because you're going to be using a sum formula. We're still talking about sum. We're still talking about an arithmetic sequence. So all good in that sense. But what you need to establish is, okay, do you have U1? Do you have N? Do you have D? Do you have UN? Do you have U1? Like what's happening, ¿cierto? So on the one hand, they want you to find the minimum integer value for X. Okay, this is the most important part. They want you to calculate the minimum integer value of X. Now, X is your new D, okay? So clearly you need to find D. Yeah, so we're probably using the equation on the left. So can I plug in N and U1 and S of N? If you plug in these three things, you can find X. If you're a little bit confused by that, just follow the process for now. See, identify you're gonna use one of these formulas, write out the variables you need, and write out the variables you have. So D equals X, you're trying to find X. Do you have, for example, U1, right? Well, they still tell you that you make 10 pendulums on the first day, so U1 is still going to be 10. On the other hand, we're still talking about a total of 15 days, so N is also going to be 15. Bada bim, bada boom. And last but not least, they tell you that Dinah would like to have at least 1,000 pendulums available. So, if she needs to have at least 1,000 pendulums available, then S of n has to be at least 1,000. Now, when we talk about at least, technically, I guess I would say S of n has to be greater than or equal to 1000, okay? If I were to get a little more technical, that's what I would say. But at least 1,000 pendulums available to sell means that S of n, we're going to leave it as, well, at least the 1,000. So boom, once you establish that, you realize you can use the equation on the left, and that will help you find D. So if you plug in everything on the equation on the left, yeah, so this would be now for part C. So for part C, if you plug in all of this stuff that I'm putting right here in, I don't know, red, ¿cierto? If you plug all of this into that equation, what you end up with is 1,000. And you need, yeah, we'll put it equals. So equals 15 divided by 2, because n is 15, parentheses 2 times u1, which is 10, plus n, which we're calling 15, minus 1, times d, which is going to be x. So from here, this does look absolutely nasty. This does look terrible. There are a bunch of parentheses. There isn't 1,000 rolling around. But how many variables do you have? You only have x. So that means that you can reach x equals an actual number. So the main idea here is that you figured out a way to create a formula that only has the variable that you're looking for. And the big brain play, in my opinion, was realizing that you can plug in 1,000 for S of n. And so that is what I mean by use the formula booklet, be familiar with it, because that's the sort of tip or trick that you gotta know that you can use. Okay, and the only way to really train that is to be quick with the formula booklet, is to understand the formula booklet and really know how it works from beginning to end. Got it? So that means I can find the value for x from here. Getting it alone is a little bit annoying, but let's see what we can do. Okay, so what I imagine most people would do from here is that they would simplify everything piece by piece. So 15 divided by 2 is going to be 7.5. Parentheses 2 times 10 is 20, plus 14 minus 1 is 14. And this 14 won't be multiplying the x, so we will just leave it as 14x immediately, plus 14x. Now from here, you want to, there's more than one way, but what I imagine most people would do is multiply and distribute this. So if I do that first, I end up with 1,000 equals 7.5 times 20, 150, plus 14 times, that's 7.5, 105, 105x. So if you do minus 150 and then minus 150, you end up with 105x equaling 850. I'm pretty sure about my thought process, but let's be honest. The day of the test, you plug in everything into your calculator, so let's replicate that. 105x equals 850. Divide by 105, divide by 105. You end up with x being equal to 850 divided by 105, 8.09. So basically, in order for Dinah to reach 1,000 pendulums by day 15, this formula tells me that she needs to be, her common difference has to be 8.09. So if she creates around 8.09 pendulums, if her common difference is 8.09, so if each day she creates 8.09 more pendulums than the day before, she's going to reach 1,000 by day 15. But the issue is, can you make 0.09 of a pendulum? How does that work? That is why over here they wanted you to answer what I have in pink to calculate the minimum integer value of x. So something I didn't talk about earlier, but I will now, is that an integer, ladies and gentlemen, this does show up a lot, so make sure you know it. An integer is essentially a whole number. and a whole number that can be negative, so -2, -1, 0, 1, 2. A whole number that can be negative or positive, but only whole numbers. That it? So, the minimum integer value of x, think about it this way. If you ended up with x equals 8.09, the common mistake is that people say, you're closer to 8, so my final answer is x equals 8. But if you take this equation, ¿cierto? If you take this equation right here, and you, instead of putting d equals 6, you put d equals 8, which would be rounding down, which is the common mistake, you end up with less than 1,000. And so the minimum integer value of the minimum integer value of 8.09, in order to still get at least 1,000, you have to round it actually up. So that's a little bit of a context trap, a pretty common thing that happens. That x gotta equal 9 in this case. Another common example, just in case you run into it, is like, I don't know, Michael is painting a fence. And you're trying to figure out how many days Michael takes to, how many days Michael takes to paint that fence. Okay, so how many days does Michael take to paint that fence? And your answer ends up being, I don't know, 5.2 days, right? And so if Michael goes to his boss and says, yo, you gotta pay me for 5 days, that's not exactly accurate, because on the 6th day, he worked for 0.2 of that day. So if he worked for 5.2 days, you can't round it down to 5. You're not getting paid for that other day, ¿cierto? So you gotta round it up to 6. Fair is fair. He still showed up at 8 a.m. to work, ¿cierto? So in that sense, for context, a lot of times you end up rounding maybe up in the direction that maybe doesn't make too much sense for you, because how the heck do you round from 8 to 9 here? From a mathematical standpoint, you don't have too many arguments, but context-wise, it makes a lot of sense. If Dinah still wants to reach 1,000 pendulums, she will have to do a common difference of 9. She's not gonna reach it with a common difference of 8. And if you really want to check your work, just plug in a 9 right here, and you will see that you have over 1,000. All right. So I think I can't leave it more clear than that. I'm just explaining why they put that thing in pink over here. And it's pretty common for you to answer like that for a context questions and stuff like that. See? So for part C, we will be saying that we ended up with an x equals of 8.09, but rounding it to the minimum possible integer value, we have to say that x equals 9. Okay? So this right here will, I cannot put it in blue like I want to. Let me try one more time. So maybe from here. Yeah. This is my answer for part C. And if you check the answer key, it literally says, you gotta prove that you understand that although you got 8.09, you gotta end up with x equals 9. ¿Vale? So 1 method point for, once again, using the formula, get to know the formula booklet well, and then 2 answer points for understanding that you gotta round it up. See? 1 answer point for what you got from the formula, another answer point because of the context and the thing that I put in pink. So very important what they put in pink. It's literally worth a whole point. All right, let's keep going. So from here, now we have that Dinah tests one of her pendulums. She releases the ball at the end of the pendulum to swing freely, and the point at which she releases it is shown as the initial position on the left side of the following diagram. So the initial position, clearly, as you can see, is right there. Yeah. Dinah begins recording the distances traveled by the ball after it has reached the extreme position. So the U1 that they're putting right here is there, ¿cierto? So notice, this swing is U1. This swing is U2. This swing is U3. This swing right here is not U1, okay? Have that in mind, it might become relevant, ¿vale? So U1 is 17.1, U2 is 16.245, U3, we don't have it yet, not it? But those are my first 3 swings. So again, context-wise, a lot of you are probably thinking in your brain, isn't this technically your first swing? And although I completely agree with you, nobody cares. The first swing is whatever the exercise is telling you. They're telling you that the first swing is when it comes back after reaching the extreme position, which is this right here. So after reaching this extreme position, your first, second, and third are every back and forth from there. Yeah. They tell us that on each successive swing, the distance that the ball traveled was, will you look at that, 95% of its previous distance. During the first swing, so first swing that Dino recorded, the ball traveled a distance of 17.1, and during the second swing that was recorded, it traveled a distance of 16.245. So before even jumping into parts D, E, and F, we can already say if we're talking about 95%, well, this is clearly not like D equals 2 or D equals, I don't know, -3. We're talking about 95%. And so think about it this way. If we're not talking about +2, +3, +4, or -2, -7, -6, then it has to be a geometric sequence. So that's the first thing we can establish. It's a geometric sequence. Now, how does the geometric sequence work? Well, I did give a quick sort of trailer earlier. It's multiply or divide. You talk about a common ratio, and the example that I gave was R equals 2. R equals 2. Now, think about it this way. If R were equal to 1, if R were equal to 1, well, what would happen? If R were equal to 1, it would be a little bit troll, but let's understand what happens. So if R were equal to 1, you do times 1 each time. So that means you end up with 2, 2, 2. So R equals 1 doesn't make much sense. ¿Vale? However, if you change it just a little bit from around 1, ¿cierto? So if you change it from R equals 1 to R equals 1.05, well, what happens now? So each time you're multiplying by 1.05, and so what happens then? ¿Cierto? Well, let's actually fill it in and see what happens. So this 2, this first term is 2, ¿cierto? So 2 times 1.05. The second term ends up as 2.1. And then the third term, so again times 1.05, ends up as 2.205. And then if I multiply again by 1.05, you end up with 2.31. All right, you guys, here's the main idea I'm trying to show you. So if you multiply by R equals 1, nothing happens. But if you multiply by R equals 1.05, what's happening is actually a 5% increase. So this guy's talking about this because he wants to talk about percentages. Yes, as you've probably seen in probability, 1 is 100%. 0.5 is 50%, and 0.05 is 5%. And so if in this exercise they are talking about that each previous distance, thing, swing, whatever, is 95%, then they're saying that R has to be 0.95. So that's the first big thing I will mention. If it's 95% of its previous distance, R equals 95. Which is much different than if they say 95 less. Okay, so notice, if they were saying 95 less, then R would be 1 minus 0.95. R would be 0.05. So that would be 95 less. It's a huge decay, okay? Over here, technically your decay is simply 5%. So you end up with R equals 0.95 because you do 1 minus 0.05. So the decay is pretty small. It's only 5%. Don't confuse that. See? It's pretty common for people to say 95% less, so they do 1 minus 0.95, you end up with 0.05, and this is a huge decay for an R value, ¿cierto? For your R common ratio, I mean. ¿Dale? Here they're saying it's 95% of its previous distance, so the decay is only 5%. R equals 0.95. Very important difference. Watch the language. It is essential in this exercise. So R equals 0.95. And they tell us that the first swing, which is right here, so the first swing, what we will call U1, is 17.1. ¿Cierto? And then for some reason, maybe it becomes relevant, maybe not. They also tell us that U2 is 16.245. So this is all we have. You have U1, you have U2, you have R. So let me put in maybe pink what we have. You have R, you have U1, you have U2. Enough blah blah, let's get into it. For part D, you need to calculate the distance that the ball traveled during the 5th recorded swing. So this is awfully similar to the stuff that they're asking up here in terms of procedure. For part D, much like part A, they're asking for the distance for the 5th recorded swing. They're not asking for the sum of the distance and the total of this or that. They're only asking for U5. They're only asking for U5. And so they're asking for the nth term. They're asking for the 5th term. So here, we can use the nth term of the geometric sequence, which is right here. Now, clearly, I have run out of space over there, so let me bring it over here. So for part D, we have that the formula is UN equals U1 times R to the power of n minus 1. All right, cool. So we have R, we have U1, we have U2. You're trying to find U5. So the moment that you plug in U5 over here, well, clearly this n right there is the same n that's right here. So the moment you plug in U5, that means you have U5 equals U1, which is 17.1, times R, which we know is 0.95. And then this n is the same as that n here. We established that n equals 5. And if we plug in 5 there in red, we're going to plug in it on the exponent as well for that n up here. See? So you define n, follow through and plug it in for everything. There is my formula. Let's plug it into the calculator because no one knows how to do that by hand. And if you did, well, I highly suggest you use the calculator anyways. Plug all of this into your calculator and smile because you just got some free 3 points. So U5 gotta be 13.928. 13.928. If you wanted to do significant figures, you would count 1, 2, 3. Do you round it up or keep it the same? You round it up. So significant figures, if you'd like, you can leave it as U5 equals 13.9. Here's the answer so that you keep on trusting me. There's the method point of using the formula. Bada bing, bada boom, that is for part D. For part E, you need to calculate the total distance that the ball traveled during the first 16 recorded swings. So now we're talking about total distance. Again, same procedure as part B. Now we're talking about the sum of the total distance. So clearly, they're looking for S of n, right? Now, they're talking about the first 16 recorded swings. So technically, that helps me establish that they're looking for S of 16. So for part E, my formula for sum of distance, my formula for the sum of n terms of a geometric sequence, there were 2 formulas I can use. And much like I established earlier, it doesn't matter which one you use because they're asking for the exact same stuff. Okay, they both ask for U1, R, and N. They both ask for U1, R, and N. So you can use either or, it doesn't matter. Just to be a rebel, I'm going to use the one on the right. Okay, whatever, I'm going to use the one on the right. And so for part E, yeah, we can do it over here, that's fine. So for part E, our formula is S of n equals U1, parentheses, 1 minus R to the power of n, divided by 1 minus R. Dale? Quick disclaimer, r cannot equal 1. Well, because as I showed earlier, it would be a geometric sequence that's a little bit troll, that's not really changing. But more importantly, it's because your denominator would end up as 0. You can never divide by 0. Okay, so that is one small, not too important detail, but just so that you feel calm. Why can r not equal 1? Because your denominator would equal 0, and you cannot divide by 0, no matter how hard you try. Okay, so this is my formula that I will be using. What do I need to plug in? You need to plug in S of n, or maybe find S of n, ¿cierto? I don't know, whatever, ¿cierto? Or these are the things, let's think about it this way. These are the things you can plug in. You can plug in S of n. You can plug in U1, you can plug in R, and you can plug in N. And so right now for part E, because we're looking about, I cannot English today. Because we're trying to find the total distance that the ball traveled in the first 16 swings, that means that N has to be 16. That means that R is still the same R as before, 0.95. And that U1, it's still the first swing, U1 is still 17.1. And so S of n is actually what we're going to be finding. So if we plug all of this into the formula, you end up with S of 16, because N is 16. So this N will go here, and it will go there. So S of 16 equals U1, which is 17.1, parentheses 1 minus R, which is 0.95. This is a 9, to the power of N, which is 16. Close parentheses, divide by 1 minus R, which is 0.95. So put all of that into your calculator, because might as well keep it friendly. Alpha y equals, then the first one for a fraction. We can put 17.1, parentheses 1 minus 0.95. And only the 0.95 is to the power of 16. ¿Cierto? Small but important detail. So only the 0.95 is to the power of 16. You close the parentheses, and in the denominator you do 1 minus 0.95. Go ahead and press enter. S of 16 is whatever that is. So S of 16 equals 191.4766. 0.4766. So if you count in terms of significant figures, do you round it up or keep it the same? You can keep it the same. So S of 16, you can leave it as 191 if you'd like. Either of these work, just so that you keep believing me. There it is, there it is. Don't forget your units. Whoops, this is all in centimeters. So my answers up until now, I forgot to put them in blue, but here I go. For part D, it's this or this. For part E, it's this or this. Okay? Yeah. Last but not least, for part F, we need to calculate the distance that the ball traveled before Dinah started recording. So this one is a little bit more big brain than the other ones. Okay? This one is a little bit more creative, and you gotta understand exactly what it's asking for. So the distance that the ball traveled before Dinah started recording. So the big thing here is that they're telling you before Dinah started recording. And so when did Dinah start recording? She started recording after it reached the extreme position. So this first line here, this first swing, is not recorded. And the ones that were recorded are U1, U2, U3, which is every back and forth that happens after that. ¿Cierto? And so the one that they're trying to find for part, whoops, went a little far. For part F is the distance that the ball traveled before Dinah started recording. So you can think about it as like the actual initial swing. I know that context-wise, we've been treating U1 as sort of like, quote unquote, the second swing, ¿cierto? Or the first one after reaching the extreme position. But right now, we need to find the distance traveled by this not recorded swing. And so the cool thing about geometric sequences is that, think about it this way, ¿cierto? So you have U1 and U2. So you have U1 and U2. You know that U1 is 17.1. You know that U2 is 16.245. And you know from the exercise that R is 0.95. And so the big concept that we need to understand here is that much how I showed it visually up there, if you write it out, as, for example, oh, your U1 is 17.1 and your U2 is 16.245. Well, you know that your R is 0.95, so you know that going in this direction, you have a times 0.95. And you can actually double check this. Okay, so let me make a little bit of space. Technically, this is your U1. U1 is 17.1. 17.1. U2 is 16.245, and you know that U1 times your R has to give you U2. And you can actually check that. So 17.1 times 16.245. Well, whoops, I'm trolling. I'm trolling. Hold up. 17.1 times your common ratio, so 17.1 times 0.95 should be giving you 16.245. And so that's if you multiply, ¿cierto? And now, and let me check this, but I'm pretty sure it works. It does work. Okay, perfect. So think about it this way. For the arithmetic one, whoops, this is a very important concept to grasp. So I'm going to explain it for a second. Got it? For the arithmetic one, if you wanted to go, for example, from U1 to U2, you would do +2. But if you wanted to go from U2 to U1, you would actually be doing -2. So if you want to work backwards, well, if forwards you did plus, for backwards you will do minus. Makes sense, right? Well, for geometric, it's no difference. If we're going forwards, you did times 0.95. If you want to go backwards, you just gotta divide by 0.95. Bada bim, bada boom. So this guy online, when he told you earlier, you need to associate arithmetic to plus and minus and geometric for times and dividing. It helps you to do these sort of connections. For moving forward in arithmetic, for this context at least with a positive D, you do +2, +2, +2. And to work backwards, you can do -2, -2, -2. For the geometric, in this case, if you're multiplying by 1.05, to work backwards, you can divide by 1.05. And so it's no different over here. So for U1 to U2, you multiply by 0.95. And from U2 to U1, just so you believe me, and it's right here, you do 16.245 divided by 0.95, and you end up with U1. And so if you do that one more time, divide one more time by 0.95, you end up with the mythical U0. And so 17.1 divided by 0.95, so going backwards one more time to go from U2 to U1 to U0, U0 is 18. And that is your argument, ladies and gentlemen, for the not recorded swing to be a distance of 18 centimeters. So for part F, you would say that that U0 is 18 centimeters. Your argument can simply be that U0 has to be U1 divided by R, quite literally. So U0 has to be 17.1 divided by 0.95. U0 gave you 18. And this right here is what we did right there. Okay? If you check the formula, the mark scheme over here, you're going to figure out that there's more than one way. There's a ton of different ways. And this is the way that we did. Okay? This is the way that we did it. That's what I meant to say. Dale? Your answer is 18. Put the units centimeters. That is for part F. Ladies and gentlemen, this was a thorough exercise of sequences. I hope you learned more than one thing. And more than anything, I hope it helped. So that being said, I'll see you around. Take it easy. All right, you guys. So number 3, the big thing about it, I would say, is that if you're scared of exponents, you're going to have a tough time. But once you get familiar with exponents, number 3 is actually relatively easy. So we have that a scientist is conducting an experiment on the growth of a certain species of bacteria. And so the population of the bacteria P can be modeled by the function blah. Okay? And notice they tell us a couple of things. On the one hand, we know that t is the number of hours since the experiment began, while k is simply a positive constant. They also told us, whoops, that the population of the bacteria is p. So remember, this p parentheses t, like its original version, is f of x. And so, basically, whatever's inside my parentheses is my x. So t in this case, so my x basically is going to be time. While my y is this whole thing. So f of x in its entirety right? However you say it, the whole thing is going to be y. Okay, so this whole thing is p for population. So my y in this context is simply population. That's the first thing we're going to point out. X is technically time, y is going to be population. So for part AI, we need to write down the value of p of 0. So if we're talking about p of 0, we're basically saying when x equals 0, what is y? Okay? That 0 right here is basically you're asking your function when x equals 0, what is your y? So when x is 0, well, you plug in 0 for x. In this context, x is time, my variable t, ¿cierto? So x is going to be my variable t, while my y is going to be my variable p of x, ¿cierto? O sea, p of t, sorry. Yeah, so p of 0 means I'm going to plug in 0 for t, so I end up with 1200 times k to the power of 0. Yeah, now anything to the power of 0, you guys, is simply going to be equal to 1. So 1200 times 1 is going to be 1200. Yeah. Now I know there's more than one of you saying, huh? What the heck just happened? This is what just happened. Okay. When you have, and this is what I mean, that this is a problem loaded with exponents. That this is going to happen a lot. This is the kind of thing you have to know. Okay. Let's say you have 2 to the power of 3. Okay, 2 to the power of 3, if you do some quick maths, it ends up being 8. Because, 2 to the power of 3 is 2 times 2 times 2. 2 squared is 4 because it is 2 times 2. 2 to the power of 1 is simply 2 because, well, it's simply 2, ¿cierto? And 2 to the power of 0, well, you got taught in school that anything to the power of 0 is equal to 1, so you're going to put it as 1, yeah? Now right here, ladies and gentlemen, there is a sort of pattern that we can identify, okay? Technically, if I were to go from 2 to the power of 1 to 2 to the power of 2, well, what do you have to do? You can think about it as plus 2, but this is not a pattern that's going to work because 4 plus 2 does not give you 8. What you can consider, however, is multiplying by 2. So 2 times 2 gives 4. 4 times 2 gives 8. And the same pattern is going to happen over here. So 2 to the power of 4 has to be 8 times 2, which gives 16. And it does check out. Now that makes a lot of sense, but what if I tell you, okay, now go backwards? So if you were to go backwards, 16 divided by 2 gives you 8. 8 divided by 2 gives you 4. 4 divided by 2 gives you this 2, and 2 divided by 2 gives you 1. And so this is a pattern that will always occur. You have 3 squared, it's 9. You have 3 to the power of 1, you're just dividing by 3, you end up with 3. You divide by 3 again, and 3 to the power of 0 has to equal 1. And so the pattern that is arising here is that eventually you have your base number being divided by itself. You eventually end up with 2 divided by 2. Or 3 divided by 3, etc., etc. That's why it's always equal to 1. The other way you can sort of try to remember it, or if you're a very visual person, you might recognize it, is that technically in the world of math, you always have a times 1, just like hidden everywhere. See, so you have a times 1, here you have a times 1, here you have a times 1, and eventually you're going to realize, So when you have 2 to the power of 0, instead of having this 2, you only have the times 1. See? Yeah, so that's another way you can sort of think about it, right? So this 1 means that you have 1, 2. This 2 means that you have 2 2s. This 3 means that you have 3 3s. This 4 means that you have, 3 2s. And this 4 means you have 4 2s. Okay, so 2 to the power of 0 means you have no 2s, so you have only the times 1. All right, I explained why anything to the power of 0 is equal to 1 in like a million different ways. So one of them must have convinced you, and now you understand that, okay, so this to the power of 0 has to equal 1 for part A I, P of 0 equals 1,200. And for part A double I, we need to interpret what this value means in this context. Now, first of all, I will mention that this is a classic. Okay, they love asking when x is 0, what is y, and what does it mean? Okay, I've seen this a lot in IB exams, so focus on the approach. Okay, the first thing is really consider, okay, here I plugged in x equals 0, and my x is time. So when time is 0, well, what does it mean? Well, time in this context is number of hours since the experiment began. So if x equals 0 or my time equals 0, that means that my experiment hasn't began yet. Or it's like at the first second. You can think about it that way. See? So before this starts at all, when x is 0, my y is 1,200. Okay, but what is your y? Your y is population. So, clearly in this context, we would say that the initial population is 1,200. Okay, and you know it's initial because time is at 0. Basically, we are at the start of the experiment. Okay, and if you look at the answer key, it's something very similar to that. Initial population of the bacteria. So the big word you have to go for here is initial. You know it's initial because time is at 0. Okay? All right, enough blah blah. That was for part A. Then we have that 3 hours after the experiment began, the population of the bacteria is 18,750. And through this, we need to find the value of K for part B. Now, the big thing about these sort of word problems is that you need to bring these words into math. So this line of information that I am now putting in pink is very important that we understand it. Okay? Now, what is the main way to help you understand these sort of exercises? You have to write somewhere what I did up here. You have to have very clear what is your x, what is your y. So x is time, y is population. So if here we're talking about 3 hours after, then boom, immediately you say, this is telling me I have an x of 3. As simple as that. And y is population, and here they tell me that we have a population of 18,750. So y is 18,750. Now, just to be very clear in this sense, that means I have the set of points that when x is 3, y is 18,750. That's what it's telling me. Okay, so this thing in pink is basically giving you these coordinates, these set of points right there. All right, and through this we need to find the value of K. Now, how in the world would this help me find the value of K? There's two main things I'm going to say here. The first one, is that when the IB gives you something, you have to use it, so just plug it in. Honestly, when the IB gives you something, you always have to use it. If you're in the doubt of what to do, just plug it into your equation and see what happens. And the second thing I'm going to mention, which is the more big brain approach, is right now, if I were to find the value of K from here, right, I am facing the following issue. Okay, if you try to find the value of K from here, you technically have 3 variables. Okay, technically you have your x variable, which is t. Technically, you have your y variable, which is pt, and you have your k. All right. So even if you try getting k alone from here, you still have 2 other variables going around being annoying. But if you were to plug in a set of points like this that I have right here, if you plug in a set of points, then boom, you fill in something for t, which would be 3, and boom, you fill something in for y, which would be p of t, which would be 18,750. And so suddenly you go from having, and this is the big place here, so you go from having, oh, that's very, I can't see that well. You go from having 3 variables to having 1 variable. That's the big brain play that's happening here. When you plug in the point, you go from 3 variables to having 1 variable. And if you have only 1 variable, you can reach k equals an actual value. See? Otherwise, you would be reaching k equals something something x, something something y. Not good enough, right? For finding the actual value of k, you need to get k alone. Plugging in a point helps you get k alone. Okay, that's the main message I'm trying to transmit to you. So if I go ahead and plug in k from here, let me just, there's a lot of space here. So for part B, my equation is p of t equals 1,200 times k to the power of t, right? And so part B gave me the information that I put earlier in pink, the set of points, 3, 18,750. So if I plug this into my equation, what I end up with is that 18,750. Remember that p of t is simply your y, and so this is your y, this is your x. In this context, again, this is your x, and this is your y, the whole thing. ¿Cierto? Yeah. So if you go ahead and plug in, you end up with 18,750 equals 1,200k to the power of 3. Yeah. So in order to get k alone, well, there's two things that are I can't English today. There are 2 main things that are annoying you. So the first thing that annoys you is the 1,200, and the second thing is the exponent to the power of 3. Yeah. So for now, we're gonna deal with the exponent last because no one likes exponents. Okay. So first, get rid of the 1,200. It's multiplying the k, so we will divide by it. So that means I end up with k to the power of 3 equals the 18,750. The 18,750 divided by 1,200. There you go. So k cubed equals 15.625. And from here, well, how do you get rid of a cubed exponent? Or, sorry, a variable that is cubed, k to the power of 3. What the heck do you do? Yeah, first of all, if this exercise was a lot more simpler, we would have k squared equals 15.625. Okay, this is just an example for the approach. See? So in my example, I have k squared instead of k to the power of 3. And from here, you probably know what to do. You would look at this and say, easy peasy. All you gotta do is do a square root onto both sides. This goes away with this, and you end up with k being equal to square root of this guy here. Fair enough. From here, you can't exactly square root because, I mean, you can square root, but it's in a different way. Okay, and that's the thing that I'm going to try to explain here. Technically, the example on the right, it works because when you do square root, what you're asking, okay, in terms of math, is which value multiplied by itself gives you what's inside. ¿Cierto? That is why square root of 4 is 2, because you're asking, right here you're asking, what number times itself gives you what's inside. 2 times 2 gives you 4, so square root of 4 has to be 2. That's also why square root of 9 is 3, because 3 times 3 gives you 9. And so square root of x squared, well, with what thing multiplied by itself gives x squared? X times x gives you x squared. ¿Cierto? So x squared, sorry, I should have explained it like this. So x times x gives you x squared. So that is why square root of x squared is simply x. That it? Now, when you have it to the power of 3, it's still the idea of the square root, but it's a little bit different. The idea is the following. When you're doing square root up here, we know we're thinking about any number or value or whatever multiplied by itself twice. multiplied by itself twice because technically in the world of math, there is a hidden number on your square root right about here. So there's a hidden number that we don't write it because we just assume it's there, okay? And this happens a lot in math. See, it's a little bit like, I don't know, you have x squared plus 3x plus 4. Everyone knows that this x is to the power of 1, but we don't write it because it's redundant, because it's obvious. The same thing happens with square root. All of these have a little 2 inside of them because this is telling you, yo, I am asking in terms of math, which number multiplied by itself 2 times gives me 4? Which number by itself multiplied 2 times gives me 9? Which number by itself multiplied 2 times gives me x? ¿Cierto? X squared, sorry. So that is why when people, or in your math class, your teacher wrote something that looks like this, he answered 3. Because 3 times 3 times 3 gives you 27. 2 times 2 times 2 gives you 8. And so this means that. So if you want to get k cubed alone, all you have to do is apply like the square root, but you're going to be doing it thinking with a 3 right there. Okay? That's the most intuitive way I can explain it. So k cubed, this goes away with this. K has to equal this square root with a little bit of a 3 outside. That it? Now you might already be thinking, dude, how the heck do I do that? Okay? Well, of course you have your calculator, don't freak out. Yeah. Clearly you're doing a very mathy thing, so we will be pressing the math button. Okay, you press the math button and look at that. It's right here. So this is square root when we're dealing with like a cubed. 15.625. Go ahead and enter. That is k. K is plus or minus 2.5. See? Plus or minus because we're talking about a squared square root. Technically, negative 2 times negative 2 can also give 4. ¿Cierto? Negative 3 times negative 3 can also give 9. But sorry, my bad. Because it's 3 times, it has to be positive. Yes or yes. See? Because if it's negative, it would end up as negative. Sorry, that might have confused some of you unnecessarily. Just leave it as a positive value. See? Whenever we're talking about cubed, it's got to be positive. Yeah. So k equals 2.5. And another way to sort of conclude that is that they also tell you that k is a positive constant. See? So, okay, whatever. K has got to be positive. ¿Dale? So the value of k following that is 2.5. We can see the same over here. So you can keep believing in me. I am not lying to you, at least not today. Yeah, then they tell us that the population of the bacteria, they ask us to find the population. Okay, so what is y of the bacteria 1 hour and 30 minutes after the experiment began. So what is y when x is an hour and 30 minutes? Okay, how do you express an hour and 30 minutes in terms of x? Okay, your x, we said, was time. Time as in t, by variable t. And t is in minutes and seconds. What's happening? It's in hours. So an hour and 30 minutes, there are 60 minutes in an hour. So an hour and 30 would mean we have 1 hour and a half. All right. All right, awesome. So when x is 1.5, what is y? See? So my OG function is right here. P of t equals 1,200. And now I have k, so I'm going to plug in k. So k is 2.5 to the power of t. So right now, all I have to do is ask my function, when x is 1.5, what is going to be my y? So when x is 1.5, what is going to be my y? So that looks something like this. Okay, obviously it looks nasty. No one likes exponents, but we can learn them and make it a little bit easier on ourselves. So go ahead, plug it into your calculator. You end up with this. So P of 1.5 equals 4,743.41649. If you would like to leave it in significant figures, I guess you could count 1, 2, 3, round it up or keep it the same. You keep it the same, so you can leave it as 4,740. All right. Over here, either works, right? On the left, we have significant figures. On the right, we have the full number. Do as you please. That is for part C. All right. So just a quick disclaimer. You guys have probably realized by now, a lot of this is just understanding when to plug in X, when to plug in Y, and what to do from there. I insist, write down what X is, write down what Y is. It'll be much easier to understand what to plug in. See? So, following that idea or that concept, we have that. The scientist conducts a second experiment with a different species of bacteria. The population of this bacteria, S, can be modeled by the function blah, blah, blah. So once again, we do have that T is the number of hours since both experiments began. So again, in this context, we have that my X is going to be time. We're talking about the variable T. And that Y, again, is going to be population. Just that in this case, is the population of the second experiment. So it's going to be S of T. All right? All right. For part D, we need to find the value of T when the two populations of the bacteria are, notice, are equal. Okay, this is the big buzzword we will be talking about for now. So when two things are equal, what are they doing to each other? They are intersecting. When two things are equal, they intersect. Okay, and when two things are equal, they are literally equal to each other. So if we have to, this is like the big mathy way to do it. Dale? You need to find T when the two populations are equal. So if the two populations are equal, then that means that P of T, which is my first population, has to equal the second population. Now, if I were to plug in P of T and S of T from here, well, we know that S of T is this guy. So that means I can immediately plug in like this. This is a times, this is a decimal. And we also know that P of T is this. Well, with the K, it would actually look like this right here, okay? So, if I now plug in P of T and S of T, I end up with 1,200 times 2.5 to the power of T equals 5,000 times 1.65 to the power of T. So this has been my line of logic, okay? This has been my procedure. We need to find the value of T when the two populations are equal. So look at this. Here's population 1, here's population 2, and I am equaling them to each other. I equal them to each other. Well, what is P of T? I have that right here. What is S of T? I have that right here. Bada bing, bada boom, plug in both, and here we are. Now, of course, this looks absolutely nasty, and this is what I meant earlier by if you don't like exponents, you're gonna have a fun time. Yes, this looks like horrifying, but the one good thing about this, you guys, is that technically on both ends, I only have the variable T. So if you only have the variable T, you just gotta find a way to get T alone and solve from there, right? Now you could try to solve it using logarithms, getting the T out of the exponent and stuff like that. But the main thing I suggest for these scenarios, especially for when you have a variable on top of an exponent, I highly suggest you use calc intersect. Okay, that is the main tool I will show you now. When you have a variable on top of an exponent, calc intersect does wonders for you, because you either use this tool here or you have to use logarithms, and no one likes logarithms. Okay, I'm just being honest. All right, so when I talk about calc intersect, I'm talking about the graphing calculator. Okay, now for calc intersect, you do have to graph your lines first. So quite literally, this will be y1 and this will be y2. When I say y1 and y2, I mean about the y1 and y2 that you plug in into your y equals. So if this is y1, 1,200 times 2.5 to the power of t, or by exponent, and the y2 is 5,000 times 1.65 to the power of t, or my x, my variable, ¿cierto? It looks like that. All right, cool. So if you go ahead and graph and you do calc intersect on both of these, you're gonna find whatever t makes this work, okay? Now, there's probably some of you that are a little bit confused by this. See, as I said earlier, when two populations are equal, they are intersecting each other, ¿cierto? So wherever they are equal is wherever they have to be intersecting, right? And so think about it this way. Wherever they intersect, they equal each other. So at the intersect, the value of t that we find is the value, is the moment in time where the populations are equal to each other. Okay, that is like the big brain play. All right, and this is mainly legal because these two variables are the same. Okay, if one of them was x and the other one was y, well, graphing it would be very, very different. Okay, but because they're the same variable, you can use calc intersect safely. All right. So I tried graphing it. It looks like this. Yours probably also looks pretty terrible, right? So all you need to do is find the intersect. Now on my window, I cannot see the intersect. So what I'm gonna do is go to zoom, go all the way down and press zoom fit. Zoom fit a lot of times helps you see the intersect. Other times you press it and nothing really happens, or it doesn't really help. But let's see if in this case it does help. All right, there's one of my lines. Oh, look at that. That seems to be the other one. All right, so judging from this, I probably have an intersect that I can barely see that's down here. See? So just to make sure that I can see it better, I'm going to be changing my window. Now, for example, all these x values on the negative side, you do not care about. You do not care about negative hours on your experiment. You only care about from 0 and beyond. Quite literally, you only care about from 0 and beyond. Okay? So on the one hand, you can change your window to have no negative values, but yes, positive ones for x. And my y min, just so that it looks a little bit more pretty, I'm going to leave it as -1. ¿Cierto? My y is my population. And if my initial population of one of these is 1,200, right? From the context from part A, II, well, then my y max, we can probably leave it as 10,000, right? That sounds about right. So that's the kind of details and stuff you gotta watch out for in order to get a much nicer window. So now I'm gonna try graphing again. There's my line in red. Now, as you can see, I still cannot see the intersect, and I'm glad this is happening because it's a good example of how it really is when you solve these problems, okay? It really is when you solve these problems, you're gonna be fighting with the calculator a lot. You're gonna be fighting with the window a lot. So get used to these tips and tricks in order to get a better window. See, a lot of times people do well in this test only because they're good at handling the calculator. I'm not even kidding. If you're good at handling the calculator, you can solve this way, way faster. See? So one way to solve this way, way faster is make this y value much bigger. And yes, end up with a graph that probably looks a lot uglier, but you will be able to see the intersect. And that, ladies and gentlemen, is all you really care about. See? It actually ended up being a pretty graph, but point is, put in big numbers. All you need to do is be able to see the intersect. Okay, you don't need a pretty graph. You're not drawing this or whatever. You just need to be able to see the intersect. That is, so plug in big numbers, plug in the values you only care about. You don't care about negative values in this context. Get a good window so you can calc intersect quicker. All right, so from here you do calc intersect. So you gotta press second and trace in order to hit calc. Go all the way to intersect. See what it asks for. It first asks for your first curve, see? So go to the left, go to the right. All right, clearly my first curve is this blue one, perfect. And my second curve, voila, it's my red one, see? Always double check because sometimes people press downwards and the first curve ends up being the same as the second curve, or vice versa. See, so make sure you double check that you're doing this correctly. First curve is blue, second curve is red, enter, enter, and here you have guess. Now your calculator is not dumb, it knows where to guess. The guess function only helps if you happen to have more than one intersect. Anytime the calculator has a guess thing, it's really asking you which intersect do you want. So clearly I want the intersect that we can see on screen. You press enter, there it is. So again, when they intersect, they equal each other. So at the intersect, the value of t that we find is the moment in time where the populations are equal to each other, and also the population we get. So using calc intersect, you end up with 3.4345687. Did I get that right? 4345. Wow, I've got some good memory. And the next one, let's see if I can get it to 27,921 167. 167. All right, awesome. So this, using calc intersect, we end up with these values. See, so this is my point. When they intersect, this is a point of intersection. So in other words, the populations are equal to each other right after like 3 hours and a half, sort of, ¿cierto? And what population do they both have? They both have a little less than 28,000 bacteria, okay? That is how you interpret for part D. So for the value of t when the two populations of bacteria are equal, you can just put in your x value, because x, as we said, x is going to be time. All right, so the value of t is the x value of my intersect, 3.4345687. If you want to leave it in significant figures, you just gotta count 1, 2, 3, round it up or keep it the same. You keep it the same. So t, you can also leave it in significant figures as 3.43. Don't forget your units, hours. If we go over here, all good right there. All right, so notice for the method point, all you have to do is equate p and st, see, which is literally what we did right here. And then how to solve it, well, it kind of leaves it up to you. And calc intersect for me is the friendliest. All right, so I hope it helped. That would be for part D. All right, only 2 more parts, you guys. Hang in there. Then they tell us that it takes 2 hours and m minutes. So 2 hours and m minutes for the number of bacteria in the second experiment to reach 90,000. And through this, for part E, we need to find the value of m, giving your answer as an integer value. The first observation I'm going to do is that for part E, you need nothing from part D, nothing from part C, nothing from part B, nothing from part A. And this is a classic for paper 2. Paper 2 oftentimes mixes 2 problems into one question. Like from A to D, it's its own thing, and from E to F, it's probably going to be its own thing as well. See? So if you're having trouble from A to D, be on the lookout for these kind of switches. Here it's only talking about the second experiment, so you don't care about the first. You can probably solve it without having to without using anything from A to D. So keep that in mind, you guys. If you're clawing for points, that can be a good test-taking strategy. All right, realize that there are 2 exercises within one, and you can't skip the parts to get points wherever you can. See? Maybe another test-taking strategy is realizing, this is worth 4 points. So maybe I might as well invest my time there. You don't need parts A through D. Maybe you want to start there. I don't know. I'm just saying that's a kind of tip or trick that can give you those extra points that you might need. Dale? Yeah, so once again, they give you a y of 19,000, see? And the x, they sort of give it to you. They tell you it's 2 hours and something. So you know that x is 2 point something. okay? So really all you have to do from here is just find, plug in y equals 19,000, find your x, and figure out how to give your answer as an integer value. Just a quick reminder, when we talk about integers, you guys, it is simply whole numbers, positive and negative. So integers will be -3, -2, -1, 0, 1, 2, 3. Right? Integers are whole numbers. If we were talking about, I don't know, natural numbers would be all of these except for the negatives. Okay? So keep that in mind. Integers is just whole numbers. That you don't want a decimal here, you want the whole number. So for part E, all I have to start off with is that my population is 19,000. So my second equation is S of t is right here, right? So S of t equals 5,000 times 1.65 to the power of t. So if they tell me that my population is 19,000, well, what does t have to be? ¿Cierto? So 19,000 equals 5,000 times 1.65 to the power of t. Now, once again, I'm facing the issue where we have a variable on top of an exponent, so I can do calc intersect once again. So I can call this y1, I can call this y2. The procedure is the same, okay? So from here, well, y2 is already written in. I just gotta change y1 to be 19,000. The window is probably gonna be okay, so let's go ahead and graph. There's my y1. It's a horizontal line, makes sense. There's my y2. See? It's a horizontal line because all these different points are different x's, but with a y that is always 19,000. ¿Vale? So here is my intersect. Just gotta do calc intersect. I already explained all of this. So this is your first curve. This is your second curve. Guess anywhere because there's only one on screen. There it is. So the intersect we got from this was 2.665, 8685, comma 19,000. All right, you guys. So this is the amount of hours. See, so technically I have 2.6658685 hours. Now what they want us to answer is to answer with hours and minutes and leave it as an integer. So technically, if I were to like spread this out a little bit, you end up with 2 plus 0.6658685, right? Now this is in terms of hours, and this is also still in terms of hours. If I wanted to pass this to minutes, well, what do you have to do? Clearly, the 2 hours, all you have to do is multiply by 60 because there are 60 minutes in an hour. So if you do 2 times 60, you end up with 120 minutes. Right? So the 2, if I were to pass it to minutes, from 2 hours to minutes, and it ends up as 120 because you do times 60. And this, if you were to pass it to minutes, you also do times 60. Ah, okay, that makes sense. So 0.6658685 times 60. There it is. So that would be 120 minutes plus 39.9521. 1 minutes. See? Now, because they want it as an integer value, we will be rounding up using significant figures and stuff like that. And so clearly, my biggest integer from here, I gotta compare the 9 that's next to the decimal. So this guy, do you round it up or keep it the same? You round it up. So if you were to leave it with integers, you can leave it as 120 plus 40 minutes. See? All right, so in this context, so it's 120 plus 40 minutes. That means that it's 2 hours. So it's 2 hours plus 40 minutes. And what they were asking for earlier is they know it's 2 hours and m minutes. And so through here, you just found out that m has to equal 40. And if we check over here, they do seem to agree with us, 40 minutes right there. There is more than one method. The most important one that you will see anywhere though is first trying to find out what the heck is going on with t, or replacing t with some other thing, etc. See? So hours was method 1. First we found our value for t, and then we got to multiply by 60 in order to convert it to minutes. So remember, 1 hour is 60 minutes. That's the big thing you have to know. That is not in your formal booklet, but you should know by now. Okay? All right. So there you go. That is for part E. Last but not least, they tell us that the bacteria in the second experiment are growing inside of a container. The scientist models the volume of each bacterium. So on the one hand, we have the volume of each bacterium in the second experiment to be this. And also the volume inside the container, so volume, is going to be that. Okay, so one is the volume for the bacterium, one is the volume for the container. Let me color code this a little bit better because it probably will be more important. So one of them is volume for, what's in green is volume for bacterium, while what is in blue is volume for the container. And so for part F, we need to determine how long it would take for the bacteria to fill the container. Now, this is way easier than what you think, but I need to explain one or two things before that. See? What's probably happening to you right now is that you're looking at those numbers and you're saying, what the heck even is that? See? Guys, whenever you see something like this that is 10 to the power of something, especially if it has a negative exponent, ¿cierto? Here we have what we call scientific notation. So first, let's make this a little bit more friendly, okay? The cool thing about scientific notation and why people do this is because this number has a lot of zeros. See? This one also has a lot of zeros. In fact, if you were to put that into your calculator, it's 2.1 times 10 to the power of -5. Not even your calculator likes putting in the zeros. See? What's happening here, technically, right? Let's go piece by, let me explain this in a different way. See? Imagine this was only 2.1 times, just so that we understand what scientific notation does. ¿Vale? Imagine you have that 2.1 and you only do it times 10 to the power of -1. ¿Vale? So if you have that 2.1 and you multiply by 10 to the power of -1, really focus on the decimal. So here we pass from having 2.1 to having 0.21. And if you were to do the same thing again, right? If you take this and multiply by 10 to the power of -1, you move the decimal place again. So each time you multiply by 10 to the power of -1, you're moving over the decimal place. So if we have 2.1 times 10 to the power of -5, technically you have to move the decimal place 5 times to the left, following the pattern I just showed you. So moving it 5 times is 1 time, 2 times, 3 times, 4 times, and 5 times. So your decimal place would end up here. That means you end up with 1 0, 2 zeros, 3 zeros, and 4 zeros. Got it? Well, technically the initial 0 point something. See? So from here, what you end up with is actually that 2.1 times 10 to the power of -5 has to equal 0.000021. Okay, that's the first thing we're going to talk about. This, in terms of scientific notation, you can just rewrite it like this. It's a lot friendlier. I suggest that you do that. See? So this is going to be for volume container. So the volume of the container is simply this number here. let's follow the same idea, but for the volume of the bacteria, we need to move the decimal place 18 times. Okay, that's definitely a little bit annoying, but at least visually, so that we're all on the same page, I'm going to go ahead and do it. See, so if you have 1.0, that it, and you do this 18 times, you end up with 1 time, 2 times, 3 times, 4 times, 5 times, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Here's the decimal point, and technically a 0 initially. See, so it's going to be 0.00000. Okay, clearly you're probably thinking, man, it's crazy to do it this way. Why is this guy doing it this way? I'm doing it this way so first you understand what scientific notation is doing and why people use it in the first place. That is, so your actual number for the volume for bacteria is simply going to be this. Okay, so let me put that as 1. So this is your volume of the bacteria. All right, so I'm doing this just so that it's more friendly for us to understand what scientific notation is actually doing. That it? Now, for part D, let's come back to reality. They're asking us to determine how long it would take for the bacteria to fill the container. And so the first question you have to ask yourself before that is, how many bacteria fill a container? So if you find out how many bacteria fill a container, you can use that information to plug it into S of t with y, ¿cierto? And that gives you x for time. So that's the game plan. How many bacteria fill a container gives you a y. Plug into your equation, you get an x. And the x is determining how long, so x is time. That it? So that is my game plan. This is what I'm going to be doing. Dale? So how many bacteria fill a container? Well, clearly, all I have to do is take the volume of the container and divide it by the bacteria. And that will give me the amount of bacteria that fill in the container. Now, I could take my calculator and plug in some very long numbers. For example, this is the volume of the container, 0.000021, divided by the volume of the bacteria, which is 0.0000000000000000001. Okay? And there you go, right? Not the most exciting thing in the world. We could have just done this with scientific notation, but I did write all the zeros out so that we all understand what it does. Okay, I know that for a lot of you it's new, maybe you haven't seen it, so I'd rather explain it first like this. Of course, the smarter way to do this is to simply leave it in terms of scientific notation. See, so this would be the volume of the bacteria, and that is what's going to be divided by, the first parenthesis is volume of the container, and that is going to be divided by the volume of the bacteria. See? So just so that you guys believe me, here it is, and it gives you the same answer. Okay, so scientific notation, why do people use it? So that you don't write 0 a bunch of times. I wrote 0 a bunch of times so I could teach it to you more, fluidly, and that's the main idea. But really, you can treat these as numbers anyways, with the exponent and everything. Dale? So, how many bacteria fill a container? Clearly from this, you discovered that we got a really big number. See, so 2.1 times 10 to the power of 13, now it's a positive exponent. So if before I was moving my exponent to the left, ¿cierto? I was moving it to the left in both cases. Now I gotta move it to the right. So 2.1 moving it to the right 13 times is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So what you actually end up with is a number whose decimal place has now moved all the way over here. That is what's happening. See, this is the amount of bacteria it takes I mean, this is the amount of bacteria you need in order to fill in the container. Got it? So you can plug in all the zeros, but for now I'm going to just plug it in terms of scientific notation. I did that for you to understand what is happening behind the scenes. Dale? So this is the amount of bacteria you need to fill in a container. So technically, if I plug that into S of t, ¿cierto? We know that S of t is this. So if I plug in 2.1 times 10 to the power of 13 equals 5,000 times 1.65 to the power of t. Now all I have to do is find t from here, and I will have solved the problem. Now, once again, I have a variable on an exponent, and the tool that I taught you is calling this y1, calling this y2, and seeing what happens. So we go to y equals, y2 is already y2, y1 now has to be this big number that I will put it in scientific notation because it's perfectly legal, and it's much better than writing a zero a bunch of times. Go ahead and graph. I'm probably not going to see the intersect. My window is probably too small. Yeah, it really seems like my window is too small. So, much like before, first try zoom fit. Sometimes you one-shot it like that. Sometimes you don't. Let's see if it does. I think it might. There's a good chance it might. Damn. Alright, well, my line in blue is my y1 and my line is red is my y2. So probably what I gotta do is give it a bigger x. See? So if I go ahead and plug in a big x, like, I don't know, whatever, 50. Maybe now it works. Let's see. Oh, there we go. See? Now, this is a great example of a graph that looks terrible, but a graph that gives you the intersect anyways. See, so this might look very ugly, but all we care about is seeing the intersect, and we do. We can barely see it, but we see it. So here you can do calc intersect. There you have your first curve, up top the one in blue. Here you have your second curve, the one in red. Here it asks for guess. There's only one, so you can guess anywhere. And there it is. So when you did calc intersect, you ended up with 44.24 8091, comma, your y1. See? So clearly in this context, my y was my population, my x was my time. Here they're asking for how long it would take. So they are asking for my x. See, so the x in this context is this number here. So that is your answer for part F. For part F, you just got to plug in that number here. Technically, if you want to leave it as significant figures, you can count 1, 2, 3. Round it up or keep it the same. You keep it the same, so you can leave it as 44.2 hours. If I show you the answer key, there it is, 44.2 hours. All right? So, as you can see here in the answer key, they do solve it, leaving it in terms of scientific notation. I did first have to explain what scientific notation was because I'm sure some of you had no idea. Now that you know, you can safely calculate it. For example, as I did over here, simply dividing them. Trust me, it's just a big number with a lot of zeros. As long as you're consistent, the answer will be the same. That it? So, ladies and gentlemen, that is for part F, and that is for number 3. I hope it helped, and I'll see you around. Alright, you guys, so for number 4, there are some very specific things we have to know. It's a sort of classic statistics problem, and let's jump right into it. So, for number 4, they tell us that it is claimed that a new remedy cures 82% of the patients with a particular medical problem. This remedy is to be used by 115 patients, and it is assumed that the 82% claim is true. And so for part A, we need to find the probability that exactly exactly 90 of these patients will be cured. So the first thing that it's a little bit hard to notice is understanding what we are dealing with, okay? When you enter the world of probability, okay, especially in the area of statistics, there's usually three things you can face at the AISL level. So on the one hand, you can sort of have like your classic probability. Okay, this is just, you know, you have a bag of marbles, pick a red one or a blue one. Yeah, that's your classic probability problem. Where it can get a little bit more specific is if you're dealing with stuff like a normal distribution. Okay, then that is a whole other world. And the last thing that we need to engage upon, that we also often maybe forget, is the binomial distribution. And so what I suggest is to train your eye to notice what you are exactly dealing with, okay? The normal distribution, it's pretty evident because the exercise will tell you it's a normal distribution or not, okay? And classic probability, you will be dealing with classic probability if it's not binomial. I mean, that's like the order of events I suggest. Notice if it's a normal distribution because they would tell you. Then figure out if it's a binomial distribution, which is a little bit harder, and I'll tell you how. And if it's not either of those, then it has to be a classic probability problem. Yeah? How do you figure out if something is a binomial distribution or not? The big hint here is that for binomial, notice it's bi, so you still have something like, I don't know, bisexual. It's one or the other. Bi for two. Bisector, I don't know, whatever, ¿cierto? So for a binomial distribution, it's sort of like you flip a coin, it's either heads or it's either tails. So a binomial distribution only has two scenarios. The other thing you can sort of realize is that the AI at the AISL level for a binomial distribution, they will be giving you three things, or at least half of them, right? They will be giving you trials, so amount of trials. They will be giving you a probability, and they will be giving you a x value. And all of this, I will explain it in a second. See? So binomial distribution is only if you have two scenarios, heads or tails. In this case, it's a binomial distribution because this remedy, it either cures you or it doesn't, period. So it's two scenarios. It cures you or it doesn't cure you. So in this case, we actually have a case of, binomial distribution. Okay, that is what we're dealing with. Now, one of the hints is the two scenarios thing that I mentioned, but the bigger hint, in my opinion, is this thing about trials, probability, and the x value. Okay, and this has to do with how you plug into your calculator. In your calculator, you will be plugging in trials, probability, and x value. So what is each thing? Well, trials, in this case, is 115. This remedy is being used on 115 patients, and you're checking to see how many times it works or not. So this will be your trials. This is the probability that it works. And the x value will depend on what they ask for. So for example, over here, if they're asking for exactly 90, then 90 is going to be your x value. And even reading ahead, they tell us for part B, the probability that at least 95 of these patients will be cured. Well, there is your x value again. So for the binomial distribution, the way it works is that they give you trials, they give you probability, and the x value is sort of like, okay, what's the probability that given these trials and given this probability, you get exactly 90? Or you get at least 95. Okay, so the x value tends to be what changes. The trials and the probabilities stay the same. And so once you realize that that is the format for binomial distribution, it's going to be much easier for you to notice it, realize that it's there, etc. The other big hint is that here it says exactly, here it says at least, and I'm going to dig upon that in a second. Why is that a hint? Because your tools, the tools that you use for binomial distribution depend on exactly that. Guys, you have two main tools, okay? Because we're talking about a distribution, you will be pressing that distribution button in blue in your graphing calculator. So you press second vars, go to distribution, scroll all the way down until you find something that says binomial, and here it is. You have two main tools, binomial PDF, and binomial CDF. All right, and instead of jumping into what PDF means, what CDF means, and all that stuff, I'd rather have you memorize or write down somewhere, okay? That intuitively you want to remember binomial PDF with the word exactly. Well, binomial CDF, it's going to be sort of like, I want to say not exactly, but maybe that's not too friendly. So if PDF is an exact amount, yeah, if PDF is an exact amount, then CDF, we can consider it like a range of values. All right, that's a lot better. So binomial PDF is for an exact value, while CDF is for a range of values. See? So if you were to draw your binomial distribution that, I don't know, I think it's something like that. I don't recall perfectly well. It's a little bit like a normal distribution, but with a slant. With a skew, I should say. So PDF is like asking your distribution like, okay, what's the probability of getting this guy there? See? That would be for PDF. The probability of this guy right here. What's the probability of landing that? Okay? While for CDF, it's a little more like, oh, from here to here, what's the probability of this? Okay, that's for CDF. Okay, visually, I will leave it like that. PDF is for an exact value, while CDF is for a range, right? All right, enough talking. So now if we jump into part A, it makes a lot more sense because we need to find the probability that exactly 90 of these patients will be cured. So clearly my trials is 115, my probability is 82%, and my X value is 90 because it's exactly 90. So do you use PDF or CDF? You use PDF because PDF is for an exact value. So you go to your calculator, you go to PDF, your trials is 115, your probability is 82. But notice this is 82%. So 82% as a decimal is 0.82. Quick reminder that 100% is 1, 50% is 0.5, and 5% is 0.05. If you memorize these three scenarios, you can convert any percent to a decimal, I assure you. So following this pattern here, you just gotta move the decimal a little bit. 82%, we're gonna leave it at 0.82. All right, it's important that you do that or else it's not gonna work. Your X value is 90 for exactly 90. PDF, because we're talking about exact value. Go ahead and press enter, bada bing, bada boom. That is your answer for part A. Quite literally, you will be putting, in order to show your work, ¿cierto? You're gonna put binomial PDF, and then in parentheses, all that stuff. So 115, 0.82, and 90. All this is telling you in parentheses, by the way, all right, is that you went to binomial PDF, and the first thing it asks for, you put 115. The second thing it asks for, you put 0.82. And the third thing it asks for, you put 90. Which makes sense, because if we go back to binomial PDF, that's exactly what we did. Whoops. If we go back to binomial PDF, it's exactly what we did. First we put 115, then we put 0.82, then we put 90. That's what the parentheses is doing. And so write this out in order to get your method point, because whoever is grading you needs to know what you plugged into your calculator and how. Okay, so very important that you put this here. It is in the mark scheme as well. See, you have to write out what you did. All right, that's for your method point. And then the actual answer, we're gonna leave it what we found earlier. I just plugged in the same thing twice, who cares? 0.053 53251. 53251. All right, which is right here, right? If you were to do significant figures, if you'd like to, you gotta count 1, 2, 3, not including the zeros. Okay, not including the zeros. 1, 2, 3, round it up or keep it the same. You keep it the same, so you can leave it as significant figures. 0.053 5, 3, 5, which is exactly what they put right here. All right, so that is for part A. For part B, we need to find the probability that at least 95 of these patients will be cured. So immediately we are already talking about CDF for a range of values. Now, this guy online told you that PDF is for an exact value, CDF is for a range of values. We're talking about at least, so you're thinking, oh yeah, this is a binomial CDF, see? And so what half the world does is that they go to CDF, they put 115 for trials, they put their probability, and then they put the X value. Whoops, they put the X value. They go ahead and press enter. They put this under as their answer, and it's actually wrong. And this is because what we haven't talked about yet is how binomial CDF works. Okay? So the first thing that I need to mention is that much how I drew here, all right, CDF, so CDF, this is for CDF, ¿vale? So CDF works from left to right. And so technically what we did just now when we plugged in binomial CDF with an X value of 95, what we said was, okay, take our take our binomial distribution, which looks something like this, okay? Find, well, our maximum is 115, right? And our lowest has to be 0, because these are our trials. And then we said, okay, find wherever 95 is. Okay, so 95, let's say, is, I don't know, this isn't exactly drawn to scale, so who cares? But let's say that 95 is like here, okay? And so with the binomial CDF, what we just did is that we found the probability of this right here. Now what the question is asking for, if we take a closer look, is at least 95 will be cured. So at least 95 cured. And what we drew here in pink was actually 95 or less cured. And that is because it's simply how binomial CDF works. Binomial CDF works from left to right. And there's a small percent of you that is staring at this problem, staring at this YouTube video saying, nah, my calculator has this fancy thing where I can choose whether it goes to the left or to the right. And I'm going to say, all right, cool. Most of the world doesn't have that. So if you have that, very good for you. That's very convenient. You need to understand that binomial CDF usually works left to right. If you have the option to say like, yo, take it from the right, even better, you can skip this next step, okay? But most of the people in the world will have to do this next step, which is basically, okay, since binomial CDF works from left to right, and I just got what is in pink, right? If I want to say at least 95 is cured, so that is 95 or above. Essentially, what you're trying to find is all the values that are 95 or above, including 95. ¿Cierto? So what you actually have to do is binomial CDF up until 94. So let's start off doing that. See? So we take binomial CDF and we say it until 94. Okay? So that's the first thing we're gonna do. We're gonna erase this ever so slightly, and we're gonna put the 94, I don't know, here. Okay? So now we found for 94, okay? And so for 94, you just discovered that the probability of this for 94 was 0.50896. So that was for 94. If you want to do like, it's just a little bit hard to explain. So CDF gave you, okay, CDF just gave me the probability of finding all my X values that were up until 94. See, because it reads it from left to right. And so if you want to find the other end of your distribution, the other end of the tail, what you actually have to do, okay, is 1 minus the left side, okay? You do 1 minus the left side. So if you do 1 minus the thing in green, in light green I mean, if you do 1 minus the thing in green, what you end up with is the part in dark green. Now why does this happen? Because way earlier what I told you was that in terms of percents, 1 equals 100%. So here what you're doing is that you're taking 100%, so you're taking the whole distribution, okay? So you take the whole distribution. When you put down 1, you take the whole distribution, the 100%, you subtracted the light green, so you have to end up with dark green. And dark green has to be greater than or equal to 95, okay? So we follow that procedure. We're going to do 1 minus what we got right there. And this is what gives you 95 or greater. See? So for part B, you have to do 1 minus that guy there. 1 minus binomial CDF of 115, 0.82, and 94, which gives you 0.491. Significant figures, you can leave it just like that. See? And if you go to the answer key, there it is, 0.491. Notice you have to do 1 minus that 94. See? So at least for me, from the visual aspect, it makes a lot more sense. Remember, you do 1 minus whatever, 1 minus the light green in order to get the dark green. See? And this is because binomial CDF reads it from left to right. So be very careful. When it says at least 95, it's 95 or above. Okay? So that's a small detail that becomes very relevant in this exercise. If you still don't believe me on the 1 minus thing, well, in your formula booklet, you actually have this thing here, complementary events. See? In the world of probability, you have to account for all scenarios. Complementary events is a little bit like the heads or tails. Okay, heads or tails. It either rains or it doesn't rain. It's either heads or it's tails. It either snows or it doesn't snow. And so those two probabilities added together have to equal 100%. And the same happens over here. ¿Cierto? Either the remedy works or it doesn't work. Either you have this side to the left of your distribution or this side to the right of your distribution. Yeah, that whole distribution got add up to 100%. ¿Vale? So, enough blah blah. That is for part B. For part C, it's fairly easy, but you do have to know one specific thing. So for part C, you need to find the variance in the possible number of patients that will be cured. Now this is actually extremely easy, but don't freak out, okay? Here's the point. The moment you read variance, this is a massive buzzword that should immediately get you thinking, okay? In the world of statistics, variance is a little bit like how much your data strays or how much your data moves around. Like, think about it that way, okay? Now, how do you calculate variance of a binomial distribution? Well, whenever you're asking yourself something as hard as that, it's probably in your formula booklet, okay? But also, you need to start accepting or understanding that variance is a buzzword, and variance is something that you need to start recognizing as something that is actually in your formula booklet, like for real, see? So, identify these buzzwords and identify these concepts that appear on problems and also in the formula booklet. So, eventually in topic 4, you will be finding the variance for a binomial distribution, which is right here. So the variance of a binomial distribution has to be, you need two things. You need n and you need p. N is simply going to be your trials, while p is going to be your probability. And I already mentioned earlier that trials was 115, so trials is 115, and probability is 0.82. So if you go ahead and plug that into the variance formula right here, you end up with 115 times 0.82 times 1 minus 0.82. So again, extremely easy problem, but you do have to realize that for variance, it's in your formula booklet. A lot of people enter the test thinking, I have my formula booklet, so I have all the formulas, like whatever. Nuh-uh, that's not good enough. You need to know what's in it, okay? Always study with it. Realize that it is an additional tool the day of the exam, okay? So there we go. We plug into the variance formula. My variance for binomial distribution has to be 16.974. If you think in terms of significant figures, you go 1, 2, 3, round it up or keep it the same. You do round it up, but if you round that up, you actually end up with 17. And so if we look at the answer over here, that's exactly what happens. You can leave it as 17. All right? So really easy 2 points. You just have to plug it into your formula from the formula booklet. Easy peasy lemon squeezy. Okay? So I guess the hard part there was realizing, that's actually my formula booklet. See, I'm sure a lot of people read this and they have no idea what to do. That is why you have to get familiar with buzzwords, with concepts that show up on your problems and in your formula booklet. That it. Study with the formula booklet. That is my main message. Study with the formula booklet. Yeah. Then they tell us for some reason that the probability that at least n patients will be cured is less than 30%, and to find, for part D, the least value of n. All right, so right now this guy online told you that you have two main tools for binomial distribution. You have binomial PDF and binomial CDF. Now in this context, we're talking about patients that will be cured is less than 30. So clearly we're talking about a range. And so if we're talking about a range, it has to be CDF. All right. Now, how does CDF help from here? Well, you go ahead and open up your distribution thing. You go to binomial CDF, and it says at least n patients. And you can't really put a variable here because, I mean, that's not how it works, right? So the first thing we need to establish is that because we're asking for less than 30, and at least n will be cured. So at least n will be cured. And that has to be less than 30. Well, you did just plug in an at least 95. And how many of them got cured? Like around 49%, right? So that is already a big hint, okay? For these exercises, what I suggest, and I've seen this in mark schemes before, so you can trust me on this, you will probably be guessing and checking. Seriously, I'm not even kidding. So if you do a little bit of guessing and checking, you will get the least value of n in this context. Yeah? So, again, right here, you found the probability that at least 95 will be cured, which ended up being a little less than 50%, right? And so what do we mean by guessing by checking? Well, if if plugging in 1 minus binomial CDF of 94 gave you around 49%, then if I go back here, so for example, we can have think about it this way. So if we do 1 minus this binomial CDF, see, we're established from part B that technically what's happening here is that this is giving you at least 95. So one above this x value, because CDF reads from left to right. See, so this is for curing at least 95. Yeah. So for curing at least 95, we got a percentage of around 49. See? But if you go ahead and increase 94 to, for example, 95, you end up with 39%. So this is decreasing, and eventually it's going to be less than 30. And this is what I mean by guessing and checking. That is, so you keep going, you change this 95 to 96, and because it reads from left to right, that means we're talking about at least 97. That's almost less than 30. Almost less than 30. So if we go ahead one more time and we change this to 97, again, this reads from left to right. So this is actually giving you at least 98. And what's the percentage of that? It's definitely less than 30. See? Right on this part here, which would be for 97, at least 97, it's a little more than 30%. And at least for 98, and for at least 98, it's less than 30. See? So the least value of n clearly has to be the last scenario that we did. See? So for guessing and checking, you can show that you did 1 minus binomial CDF of 115, 0.82, and 97. So technically what's happening here, if you want to get really fancy, is that you're doing 1 minus the probability, technically, ¿cierto? The probability that x was, it reads from left to right, so probability that x is less than or equal to 97. See? So that is actually going to end up as the probability of x being greater than or equal to 98. And the probability of that, from what you just plugged in and etc. and blah, 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 was 0.2217. So 0.22. So clearly less than 30. Now, you need to show, and here's the thing. Your guessing and checking is your method point. Okay, your guessing and checking is your method point, so you actually have to show that you were guessing and checking. Dale? So this was like your final answer. Okay, you got 22. But you gotta show that you were guessing and checking a little bit. So just to get full credit, you should also write somewhere that you did 1 minus binomial CDF of 115, 0.82, and 96. So the one that was 1 before it. And that this gave you around 30, a little more than 30%. So this gave you 0.303. Okay? And it's very important that you do this because in the mark scheme, it actually says of all the different methods, and for me, my favorite is method 2, okay, is that part of your method point is quite literally use the binomial CDF in the graphing display calculator for at least 2 different values of n greater than 90. All right, which is clearly, that's what we were spamming in the graphing calculator. But the person grading you doesn't know that. So you gotta show the person grading you, I did do that. You don't have to write them all. Writing 2 or 3 is good enough. And this right here is a very visually appealing answer, ¿cierto? You can see quite literally that I go from 96 to 97 until I go from a little more than 30% to a little less than 30%. So that would be for part D. So yes, guessing and checking here works. I've seen it in other mark schemes, and it's a suggested method. All right, and it's the one I suggest because for me it's the friendliest, pretty easy to understand. Okay, whatever. See? Then they tell us that a clinic is interested to see if the mean recovery time. All right, so this is basically like a whole other problem. Yeah, so that's the first disclaimer. In paper 2, the cool thing about it, if anything, is that usually you have 2 problems melded into one. So all of this is its own exercise, and all of that is its own exercise. So all of this up here was for binomial distribution, and all of this down here clearly has to be for a t-test. Why do I mention this? The day of the test, if you have no idea how to do from parts A, B, C, and D, we'll take a good look at what happens on the next page, because maybe you can solve this, because this doesn't care about what happens in parts A, B, C, and D. Yes, it's part of the same exercise, but it's not part of the same like problem per se, you know? This is a t-test. You talk nothing about remedies or binomial distribution or anything like that. Dale? I mean, yes, you talk about remedies because it follows the context, but you're not using anything from parts A, B, C, and D. You can literally skip to E, F, G, and H and solve it without doing anything beforehand because you don't need anything from before. That's the message I'm trying to transmit to you. So the day of the test, if you face a problem and you're stuck on the first couple parts and it's paper 2, maybe skip ahead because there's a whole other exercise waiting for you. Okay? Claw points wherever you can. Be on the lookout for that kind of stuff. So, enough blah blah. Let's get into it. We have that a clinic is interested to see if the mean recovery time, okay, so mean recovery time of their patients who tried the new remedy is less than that of their patients who continue with an older remedy. So the main thing that they're looking for is is if the new remedy is less than the older remedy. So new remedy less than older remedy. Okay. Actually, if I were to make it very, very fancy and say new remedy less than older remedy. The clinic randomly selects some of their patients and records their recovery time in days, and the results are shown in the table below. So, right here, you have the first list, or the first table, which is for new remedy, right? So group N was for new remedy, and they recorded 1, 2, 3, 4, 5, 6, 7 people. Right, so the first person took 12 days, the second person took 13, etc. And then for the old group, they had more people. They actually had 9 people that they tested. The first person took 17 days, the second one 11, etc. So they tell us that the data is assumed to follow a normal distribution with the population variance, and that the population variance is the same for the two groups. This is a little more important than what you think. And that comes into play later, okay? The bigger thing here, though, that we will focus on is that it is a t-test, or that they use a t-test that compares the means of the two groups at a 10% significance level. So I know this is a lot of blah, blah. I know that some of us are a little bit confused. So let's go piece by piece. The first thing is that a t-test, what it does is that it compares the means, quite literally. So whenever you're comparing means, you will be using a t-test. Okay, and when he talks about a significance level, it's sort of like how much how rigorous your test is. Okay, let's stick with that idea for now. So a 10% significance level is how rigorous you want your test to be. Usually we talk about 10%, 5%, or 1%. Okay, so that is something you compare with your p-value, but that will happen later. I'll explain that later. ¿Vale? For now, let's focus on part E. So for part E, you need to state the null. You need to state the null and the alternative hypotheses for this t-test. So for part E, the null is what they usually call H0, while the alternative is usually what they call H1. Now, for the null, what I need you to associate it to is that the null is usually simply like no change. Well, the alternative is going to be that there is a change. So yes, change. Now, in this context, we're comparing means, right? So if null is no change, and we're saying, if the null is for no change, and we're comparing means, the null we can leave it as same mean. So that means that between the old remedy and the new remedy, there is no difference. So it's going to be the same mean. There is no change. If there is a change, then you would say different means. All right, this is for the initial sort of intuition I need to give you. Now, this is clearly not like detailed enough. Like the IB wouldn't like this because it's just saying that your null is the same mean and that your alternative is different means. Yes, you're getting the right idea, but you gotta be a little more specific than that. So for getting the full credit, you gotta be a little bit more specific. And so it's the same mean in what sense? So for the null, what we're gonna leave it as, like our official answer, everything from before was just for intuition. So our official answer for null, we would say something like, you would say for H0 maybe that the mean recovery time between the old remedy and the new remedy are the same. Well, on the other hand, what you would say for H1, which is that there is a difference, you would say that the mean recovery time between the old remedy and the new remedy is not the same. And in this context, they're specifically looking for the new remedy being less than the new remedy having a recovery time that is less than the older remedy. So specifically here, you gotta go after what the experiment is being used for. So it's not only that they're not the same, it's actually that the mean recovery time of the new remedy is less than the recovery time of the old remedy. Dale? So in terms of words, that is how you can like sort of put it. The other way you can consider is that for H0, you would say that, well, this is gonna be my new remedy. I mean, sorry, I'm not explaining myself well. This first group is gonna be my first list, okay? Because it is the list of data. And so you will be talking about your first mean, right? So this is gonna be U1 for your mean, and list 2 will be giving you U2, which is your second mean, okay? So technically, if you wanted to put that in terms of math instead of words, although words are perfectly fine, you guys, if you were to put it in terms of math instead of words, you would say that for H0, so for H0, you can also say that the mean of your first one, right, of the new remedy is equal to the mean of your second remedy. Easy peasy. While for H1, if we're talking about the remedy of the new one being less than the recovery time of the old one, which is exactly what it says here, they're testing to see if the new remedy has a recovery time that is less than the old remedy. So that means that, well, new is U1, old is U2. So here you would say that the mean of U1 is less than the mean of U2. All right, so either of these scenarios that I'm now putting in pink will give you full credit. So you either put it like this, or you either put it in text like that. Either of them work. The main idea we need to stick to is that, as I mentioned earlier, the null, which is H0, basically talks about no change, while the alternative, which is H1, proposes that there is a change. Okay, and in this context, because we were talking about means, that is why we said that no change was the same mean, while yes change was different means. Now, in which way specifically depends on how the experiment is being conducted. In this case, different means in the sense that the new remedy has a lower time than the old remedy. All right, enough blah blah. That is for part E, and just so that you guys keep on trusting me, this is like the mathy way to put it, if you'd like to say, ¿cierto? But they also accept, notice, an equivalent statement in words, okay? So either of them works, whatever floats your boat, see? So that is for part E. Then for part F, they jump straight to the heart of the problem, find the p-value for this test. So part F, find the p-value for this test. How the heck do you do that? Yeah, this is simpler than what you think. The big thing here is that they're asking for a t-test. So you're gonna go to your calculator, go to, I think it was stat. So you go to stat because clearly this is a statistics problem. You go to tests because we're talking about a t-test, and two different t-tests will appear. You have like the normal t-test, you wanna think about that? Think about it that way, like simply t-test. And then over here you have two sample t-test, ¿vale? So you either have a t-test or a two sample t-test. If you press t-test by itself, you're gonna see that it asks for a mean and it asks for a list 1. And that's it. But here we have two lists. We have the list of the group of the new remedy and the list of the group of the old remedy. So from here, it's not a t-test by itself, it's a two sample t-test because you have two samples. So we go ahead and press here. List 1 is L1, so this is gonna be L1, all of this. All of that is gonna be L1. And then list 2 has to be all of that. ¿Vale? So we have to make sure that we do that. List 1, list 2. Frequencies is if you have a frequency table somewhere, in this case we don't. And over here, you guys, these three options, what it's technically doing is that it's asking for your alternative. It's asking for your alternative. So for the alternative, we are saying that the mean recovery of the new one is less than the mean recovery of the old one. And since we're calling U1 as new and U2 as old, this is my alternative. I need to express it right here. And so clearly I gotta press the one in the middle. All right. And then this last thing where it says pooled, we will be putting that it is pooled. Now, what the heck is pooled? What is happening? Pooled, for now, you just need to associate it to this statement right here, which they pretty much always give you. Okay, for the AISL level, in my experience, for pooled, you will always be putting yes. Okay, you don't have to exactly worry about it, but if you want to learn a little bit about it, pooled is essentially that the two samples that you're using, both of them follow normal distribution, but much more importantly for pooled, their variance is the same. That's the big thing about pooled. Their variance has to be the same between the two groups. If the variance is not the same between the two groups, you will be putting that it is not pooled. In my experience for AISL, you always put yes for pooled, but just if it ever comes up in some test or whatever, what matters here is that the variance is the same. Okay, so variance being same means that you have pooled. All right, that is what I want you to associate it to. That now, the one thing I forgot to sort of show is that we're putting list 1 as all of this and list 2 as all of that. So where the heck do you do that? You gotta go to stat and then press edit, and here are the lists. Now I did get ahead of myself and put it earlier, so you know, just double check that everything is correct, that it's aligned, etc. So here's list 1 right there, ¿cierto? And here's list 2 right over there. See? So enough blah blah. We go back to test, to sample t-test. Everything is okay. We go ahead and press calculate. We're pretty much never going to be drawing it because who cares? I mean, you can, but whatever. Go ahead and press calculate. See? You get a bunch of different values, and in this context, all they're asking for is for the p-value. See, there's a lot of stuff here. Don't get lost in the sauce. Cook only where you need to. The p-value equals 0.062. Yeah, we're going to leave it like that. So that would be the p-value for this test. It's the same one right here. All right, and then for part G, we need to state the conclusion for this test and give a reason for my answer. Now, I'm doing this on the fly. I'm actually not sure if this works, but it might help for explaining it. What if I press draw? What happens? I don't think I've ever done this actually. This might help for concluding. That's why I'm trying to draw it. Let's see. Oh, I'm drinking cold coffee right now. Not the best. But, you know, gotta do what you gotta do, right? Oh, wow. That's actually pretty good. Not gonna lie. Yeah, so here, wow, calculator's gonna do a lot of stuff. Here I graphed my distribution, okay? And I did a 2-sample t-test, and I got a t-value and a p-value. Now the t-value and the p-value, what they both do is that they help you conclude the test. All right, how do they help you conclude the test? So here's the main idea that I need you to understand. Right now we have my binomial distribution that looks something like this. See? And we were talking about this is our alternative. See? And basically what this does is that you're going to be looking at the left side of your distribution. See? Just trust me on this. It's just going to be to explain what's happening. That it? Now, and this actually partly is also going to answer part H, so pay attention. That it? How do you conclude this? What is happening? What do the numbers mean, Mason? Mason, what do the numbers mean? So, in this context, okay, there are two main ways in which you can conclude your answer. One of them, okay, is to compare. Okay, so for concluding, ¿vale? One method is to compare significance level to your p-value. Now, why do you compare significance level to your p-value? Because both of them are percents. Both of them are probabilities, okay? And the other way that you can sort of try to conclude is that you need to compare the critical value to your t-value. And why would you do this? Because technically both of these will be a sort of benchmark. Yeah, I'll explain both of these individually. See? So imagine you do this binomial distribution. It looks something like this. And let's say that your significance level, actually, let's apply it to the context. So your significance level, they tell you that it's 10%. ¿Vale? So that means that you're going to be drawing a line somewhere, let's say right here. And you're going to say like, okay, so this line, actually, no, it's the other way around, my bad. So for significance level, they tell you, so your significance level is 10%. So what you will do in theory is that you will count all of this area until you reach 10%. So you count the significance level until you reach 10%. ¿Vale? And so what the p-value does, so our p-value was just around, how much was it? 0.062 in percent, so 0.062, ¿cierto? If you were to pass it to a percent, it's actually 6.2%. ¿Vale? All you have to do is move this decimal place 2 times to the right. So the p-value we know is 6.2%. ¿Vale? So then over here, around there, ¿cierto? Is going to be my 6.2%. So what does the p-value mean? ¿Vale? This helps for part H, but really helps more for part G to understand how to conclude stuff. So what the p-value does is the following. Actually, the Marx team puts it in a really good way. So here they tell us that the p-value is basically, so this is for p-value. The p-value is basically the probability of obtaining the results as those observed, given that the null hypothesis is true. So basically, if your null is true, the probability to observe what you're observing is your p-value. And so in this case, basically what's happening, okay, is that assuming that the null is true, and remember that the null was no change, so assuming that there's no change, assuming that the remedies don't matter, the probability to observe what I am observing is 6.2%. And remember, I did tell you that significance level was how rigorous your test is. And so essentially, what's happening here is that the experiment was conducted. They said that the significance level is 10%. So essentially what they're saying is that anything less than 10% is a little too extreme. And if it's a little too extreme, then it's a little bit too crazy. And if it's a little bit too crazy, then it's a little bit too unlikely. And that is when the null hypothesis stops working. Because the null is basically saying, there's no change like between one remedy or the other, it doesn't matter. But what you're observing has such a low probability of occurring that your null gotta be wrong. Okay, that's basically what it's saying. Your null has gotta be wrong because we were expecting, or we would be surprised, right, if there was a 10% chance of seeing what we're seeing, but we're seeing what we're seeing with a 6.2% chance. So that's a little bit too low. It's a little bit too extreme. And essentially, the null has got to be wrong, ¿cierto? And so you compare the significance level to the p-value because they're both percents. They're both probabilities. P-value is less than significance level. And now this is for part G. So p-value being less than significance level means that the values are too extreme. Okay, so value is too extreme, assuming that null is true, right? And so if the p-value is less than the significance value, the values ended up being too extreme, which means that the null is wrong. So if the null is wrong, you reject HO or H0. See? Because the values are too extreme, you reject HO. So for part G, the conclusion of your test is that you reject HO, and the reason for your answer is exactly what I'm putting now in red. That is your justification, which is literally what they do in the mark scheme. See? They compare, right here, they're comparing the p-value to the significance level. Okay? So I guess if you want like full credit, you would have to plug in the numbers here and say, okay, this is 6.2% being less than that 10%. Okay, so clearly you have to reject HO. That is the first way to conclude using significance level with p-value. Essentially, you're comparing percents, comparing probabilities. That it? So that was for comparing probabilities, what's in pink and what's in black. Technically, not in this case. I mean, I already finished G and H. You can go, you can have a nice day. But just so you know, I did say there are two ways to conclude. Either comparing percents and probabilities using significance level and p-value, or comparing critical value to t-value. That's also why my calculator over here gave me a t-value there and a p-value here. It's telling me, dude, conclude your answer either using the percents or using the benchmark. ¿Vale? And here's the main idea. When the exercise talked about the significance level of 10%, if you draw in that 10% here, ¿cierto? Well, it's gonna stop somewhere. And so wherever it stops, right here is where you can actually put your critical value. And so the other way to solve this is that at 10% significance level, you discover a critical value, ¿cierto? So right where the 10% stops is where your critical value is going to be, and this is your benchmark. So anything to the left of your critical value is going to be too extreme. And so the other way to conclude is that if your t-value is, well, in this context, we're talking about to the left. So if the t-value is less than the critical value, ¿cierto? Again, you would be rejecting, right? In other cases, it might be that the t-value is greater than the critical value if we're talking about, I don't know, this side of the test, ¿cierto? So if your critical value happened to be over here, then you would have to be considering some value that ends up over there. See? Point is, you either compare the probabilities or you compare the benchmarks. The probability is what gives you the benchmark is what gives you the probability. Vice versa, it works the same. In either case, you are always exploring, and this is the main idea of the p-value, if your values are too extreme. So again, p-value is assuming that your null is true, and if the probability of seeing what you're seeing is too low, it's too crazy, it's too extreme, you reject the null. Okay, so reject the null. All right, ladies and gentlemen, enough blah blah. I hope I cleared up one or two doubts. That would be for number 4. All right, you guys, we have that for number 5. A particular park consists of a rectangular garden of area A and the concrete path surrounding it. So this A right here is going to be for the area of the garden. So area A for a garden. And they also tell us that we have a concrete path surrounding it. The park, so this is for the park, which I'm going to be putting in blue. The park has a total area of 1,200. So one thing is the area of the garden, which is this guy right here. And another entirely different thing is the area of the park, which is not only what surrounds it, but also what's inside. Okay, so for the area of the park, it's the path plus the garden. Well, the area of the garden is, of course, only the garden. What else do we know? We know that, for example, the width of the path at the north and south side of the park is 2 meters. So this 2 meters that is written right here is also going to be right there. Make sure that all the information they give you is actually in your diagram, because it might help you down the road for interpreting the exercise. So that too is up here and down there. That is information that this is giving me. And also the width of the path at the west and east side of the park is 1.5 meters. So this 1.5 right here will also be appearing over there. So we have 1.5 on the left and on the right, on the east and on the west. Yeah, the length of the park along the north and south side is x meters. So this x right here, which is cutting like that, that is what we are calling x. Well, and technically this down here is also going to be x. Okay, so that might be important. You never know. And we know that these meters, or this x value, is between 3 and 300. Now, some of you probably read this and are thinking, why does this matter? And my answer to that is keep it in mind, okay? Keep it in mind that there is a restriction for the values that x can take, which actually by context, you already have one. For example, you can't have negative meters. Like x has to be greater than 0. You already have some sort of restriction. Why is this relevant? Because during our procedure, you might discover more than one answer for x, and you will end up discarding one of them and accepting one of them, given this condition here. Okay, so all that this is really doing is not here to confuse you. It's probably here to help you. If you end up with more than one value for x in one of your solutions, this will probably be the big hint for which one to accept. All right, enough blah blah. Let's jump into the exercise. For part AI, we need to write down the length of the garden in terms of x. So the first thing I need to really leave clear to you is that when they say in terms of x, that means that your answer needs to have an x inside of it. Okay, so in terms of x means that your answer has an x somewhere in there going around. ¿Vale? So if we're trying to find the length of the garden, which I'm putting in green right here, the length of the garden is this guy right there. And so how can we express this in terms of x? Well, the red line is x, ¿cierto? So the red line is x. And so if I were to express the green line in terms of x, I can clearly say that x, for part A, I, that x minus these two ends right here, minus this end, and minus this end, has to equal green. So x minus those two ends has to give me the green, and these two ends are both worth 1.5. So for the area, or sorry, for the length of the garden, x minus 2 times 1.5 will give you the length that we're drawing in dark green. Okay? So x minus 3 has to be the length of the garden, which I'm putting in this green line. ¿Vale? So I'm putting the green line to replicate this green line. If you want to get more fancy, you can just, maybe write here length garden, okay? Just so that you don't forget. So length of the garden has to be x minus 3. A very visual solution in this case, and that is why I suggest that all information they give you to actually put it into your diagram. It makes it a lot easier to see the procedure you have to follow. Yeah, so for part AI, my final answer is simply going to be x minus 3. And I'm going to put it in light blue so that we recall that this is the answer. Then for part AI, we have that we need to find an expression for the width of the garden in terms of x. So for the width of the garden, well, we just found the length of the garden. So now we have to find the width of the garden. See? Well, just to make this diagram a little bit more complete, technically up here we have an x minus 3. And for the length of the garden, well, how can I try to find that from here? All right, so you have the length of the garden, you're trying to find the width of the garden, but you don't have the area of the garden yet. And so if we try to solve this directly thinking of what you have in regards to the garden, you're not going to be able to solve it. You have to go above and beyond. And in this case, think about it this way. This line in purple, if you connect it to something else, what does it turn into? This line in purple, technically you can connect it like this, boom, which is the same as if I were to draw this line here. And so technically this line in purple that I put earlier for the width of the garden does have to do with the width, it does have to do with the width of the park. Technically, the width of the park is going to be 2 plus purple, right? Plus 2. And so width of the park, we now know is 2 plus 2 plus the width of the garden, which is the purple line. See? Just so that we're all on the same page, let me erase what's in pink because it might be a little bit confusing. The width of the park, so this whole section here, right, has to be 2 plus 2 plus the line that I'm putting in purple right there. Okay? So the width of the park, of course, has to be 4 plus the line in purple. Yeah? And just so that we all sort of maybe keep this clean, we're going to call the line in purple y. Okay, so the width of the park has to be 4 plus that y. Yeah, so how can I try to find y? Because at the end of the day, we're going to find an expression for the width of the garden, which we're not calling y, in terms of x. So you want to reach y equals something something x. Dale? All right, so the width of the park, what do you know about it? How can you work with it? Well, you know that the width of the park times the length of the park, which is x, ¿cierto? So the width of the park times the length of the park has to give you 1,200 because the total area of the park is 1,200. So notice the procedure. You went piece by piece. Could you find the value for y just with the garden? No, because you don't have the area of the garden. Do you have the area of the park? You do. Can you put y into your formula for area of the park? You can, but you end up with a bunch of x's. Do you care? You don't care. Actually, you're happy because you want to leave it in terms of x. So from here, what you do is say, okay, the area of the park is 1,200. So for part A, double that, you will say that 1,200, the area of the park, has to equal the length of the park, x, times the width of the park, 4 plus y. And from here, you need to get y alone. Now, I guess there's a couple ways to solve this. I don't know what's the quickest way. Well, the most intuitive way for me, at least, is first you distribute. Okay, so if first you distribute, you end up with 1,200 equals 4x plus xy. So you want to get y alone, ¿cierto? Width of the garden in terms of x, so y equals something something x. You can go ahead and do minus 4x. So xy has to equal 1,200 minus 4x. From here, you can divide by x to both sides. When you divide on the right side, you have to divide everything by x. You got to be consistent. So y equals 1,200 divided by x minus 4. So bada bim, bada boom. I put it in blue because it's my answer. The expression of the width of the garden, which we did call y in purple. So we did call it y in purple. So y equals 1,200 divided by x minus, this is a 4. Okay, no one should get confused. This is a 4. Okay, and if we check the answer key real quick, there it is. Okay, so y equals 1,200 divided by x minus 4. See? Yeah. All right, and last but not least, for part A, triple I, they tell us hence, this is a very important word, show that A equals all of this. Yeah, first things first, when they talk about hence, it means, it's kind of like saying therefore. Okay, so given that you solved AI, and given that you solved a double I, find me this. And so hence is a very, very, very big and awesome hint that, hey, you gotta use what you found out earlier to show me this. Okay, so in terms of procedure, it can be a very, very big hint. So how in the heavens does finding the length of the garden and finding the width of the garden help me to find big A? Well, the first question you should be asking yourself is, what the heck is big A? So you scroll back up. Well, in your case, you're going to look back up because you have the paper in front of you. And you say, okay, what is big A? Big A is the area of the garden. And so the garden is indeed a rectangle. And so for rectangle, you just do length times width. This is pretty much common knowledge at this point. And so the length times width of the garden, as you see here, is the line in green, x minus 3, and the line in purple, y. Now you know that y is this, ¿cierto? So technically for part A triple I, it says show that big A equals this, ¿cierto? So really you just have to calculate big A yourself. So big A we know is area of the garden. And so for the area of the garden, you have to do length times width. And you know by context, or by what we figured out so far, that length is going to be this x minus 3 that's in green, while the width is going to be what we have in purple, the y. Now from part A double I, you found that y is actually going to be this right here, 1,200 divided by x minus 4. So this y turned into this here from part A double I. So notice how the hence or the thus or etc. is helping a lot with this part of the exercise. Actually, this part here is from part A single I. See, from part AI. And so I'm just insisting on the point when they say hence, it's a big hint for how to move forward. Literally in this part, you have to use, for part AI, you found x minus 3, and from part A double I, you found the value for y, okay? So when they say hence, it's a big hint, okay? Use it to your favor. All right, from here, we need to reach these numbers. We need to reach the 1212, the minus 4x, the minus 3,600. We have to figure out how to get there, see? And so the first thing we can observe is that there are no parentheses. So clearly, you gotta get rid of the parentheses, ¿vale? Whenever you have two parentheses like this, next to each other, all you have to do is multiply the first one times the first one times the second one, and then multiply the second times the first and the second times the second. Pretty classic. You should have seen it in class, by now, but what you end up with is that big A equals, well, this first multiplication is going to be x times 1,200 divided by x minus 4 times x. And then down here, you end up with minus 3 times 1,200 divided by x. So a negative 3 times negative 4, you immediately end up with plus 12. See? So from here, what can I sort of solve right away? Well, this will go away with this, ¿cierto? So there you end up with only 1,200. This is just going to turn into 4x. This is going to turn into 3,600. And this 12 with this 1,200 will add together as 1212. So at the end of the day, once you do all of that, combining like terms, etc., you end up with the 1212 minus 4x minus 3,600 divided by x. And so there, bada bim, bada boom, we have proven, or we have shown, that big A equals exactly that. You double check your answers, it looks well aligned, checks out to me. There you go with part A. Later on, they tell us for part B that we need to find the possible dimensions of the park if the area of the garden is 800 meters. So area of garden, what do you know for area of garden? Area of garden, you know that it's this right here, okay? So what are the possible dimensions of the park? Yeah, when they talk about dimensions of the park, they're talking about the length of park and the width of park. Dale? So first things first, we're gonna need a lot more space for this. So length park, we know is simply x. While the width of the park, so width park, is 4 plus y. Now we also know that y is this guy right here. So if you do 4 plus y, you end up with 4 plus 1,200 divided by x minus 4. So really for the width of the park, you're just going to end up with 1,200 divided by x. 1,200 divided by x. Yeah, so that's the length of the park. That's the width of the park. And over here, they tell us that the area of the garden has to be 800 meters. So think about it this way. Area of the garden is 1212 minus 4x, and then I think it was another minus. Yes, minus 3,600 divided by x. So really what's happening here is that they're telling you, yo, if the area of the garden is 800, this obviously has an impact in your value for x. So given the values of x that you're about to discover, okay, given the values of x you're about to discover, plug that value of x over to length and over to width and tell me how big it is. That's what it's asking for. It's telling you, find the possible dimension of the park. So find the length, find the width. If the area of the garden is 800. Now, if the area of the garden is 800, I'm plugging in 800 right here. That means I can get a value for x. And whichever value of x you find, you plug it in for length and width, and that will be your answer. So the big sort of challenge right now is that you need to solve what I'm putting in pink right now. And so how the heck do you solve that, right? Okay, there's two main ways in which you can try to solve it. See? So on the one hand, and I'm going to show you both because I think it's important to have as many tools as possible. Okay? So on the one hand, what is annoying you right now? Right now, you're probably annoyed by the fact that you have an x in the denominator. So how do you get rid of an x in the denominator? What you can do is multiply everything by x. So if you multiply everything by x, you end up with 800x equals 1212x minus 4x squared. And over here, sorry about that. And over here, you have 3,600 divided by x times x. But if you have divided by x and times x right next to each other, then boom, boom, you only end up with 3,600. So, oh, look at that. From here, maybe it turns out to be easier to solve than what you think. So from here, you want to get everything onto one side because this should be looking familiar. This should be looking a little bit like a parabola. So try to get it into the parabola equaling 0. So I'm going to go ahead and throw everything to the side on the left. That is, so if I throw everything to the side on the left, I would be doing plus 4x squared to both sides. I would also be doing minus 1212x to both sides. And I would also be doing plus 3,600 to both sides. So if you do all of that at once, trust me, what you're going to end up with is, on the one hand, you end up with 4x squared. You also end up with minus, how much is that actually? 412x, ¿cierto? And also you end up with plus 3,600 equaling 0. Now, because all of these are even, I could technically divide everything by 2. So that's just something to make this a little bit more simple. So if I were to divide everything by 2, and that's just a big hint you can always use, ¿cierto? If it equals 0, dividing this by 2 still keeps it at 0. So this is just to make the numbers more friendly looking, right? So you can divide everything, for example, by 2, right? So if you go ahead and divide everything by 2, what you are going to end up with is 2x squared minus 206x plus 1,800. And look at that, they're still all even. So I can again divide by 2, again divide by 2. So x squared minus 103x plus 900 equals 0. And from here, you've probably been here a million times. You have to solve for x. You have to solve for the parabola when it equals to 0. So there's a couple different choices you can take from here. The classic is maybe factoring. And so factoring is when you end up with two parentheses, right? It's usually like, I don't know, x plus 2, x minus 3, something like that. You can also do the quadratic formula, okay, which is in your formula booklet, which would be, just to show you the tools, formula booklet is, I'm pretty sure it's in here. I'd be surprised if it's not, I'll be honest. I'm pretty sure it's here. Quadratic function. Dude, no way it's not here. Quadratic, there it is. Yeah, so solutions for a quadratic equation, you can technically use this right here. Okay? Yeah. So that works, that's another option. But a lot of you are probably used to is simply graphing. Okay, so if you go ahead and graph this, you can find where x equals 0 because you do have it equal to 0. See? So you can go to y equals, make sure it's all clean. You put x squared minus 103x plus 900. Then you're going to go ahead and graph and try to find the values of x from here. Now it's very likely that your window is very different and you can't see it well and stuff like that. So here I can barely see it, which is probably your scenario as well, or maybe in your scenario you can't even see it. So what you're going to do, or what I suggest, is that you press zoom, scroll all the way down and press zoom fit. So once you press zoom fit, this usually helps you see the intersects. Now this might help you see the y-intercept instead of the x-intercept. Here I see one of the x-intercepts, but there might be another one because this is a parabola after all. However, pressing zoom fit can give you a better idea of how to change the window. So for example, all these negative x values, well, you don't really care about them because actually they tell you earlier that x has to be between 3 and 300. So immediately you can already say, oh, okay, so my minimum x we can leave it as 0 and my x maximum we can leave it as 310. Yeah, so that's the first thing we can do. Y max probably doesn't need to be that big. You only care about the x-intercepts. Just to leave them more pretty, I'm going to put minus 10. And y max, we're going to say whatever. I don't know, like 100. ¿Vale? So now we graph. Doesn't look particularly pretty, but I can see both x-intercepts, which is what I actually care about. See? So you can go ahead and press second and then trace in order to hit calc. We are calculating zeros. Zeros is for x-intercept. So now it asks for left bound and right bound. Make sure you find where your point is. So there it is. Let me go all the way to the left first. Yeah, so here we have for left bound, right? Then we press somewhere on the right. No one cares where. And so notice, there in my graph, we have two dotted lines. Your graph might not show it, but it's still going to ask for the left and right bound. And so what the left and right bound does is that it's going to scan within these bounds where in your function you have a 0, where in your function you have an x-intercept. And so the guess, it's not because your calculator is dumb, it's because in case your bounds had more than one x-intercept, this guess would allow you to choose which. Okay, but I'm going to press enter around here, and x has to equal 9.64. We can, significant figures, we can just leave it as 9.64, honestly. So this is one of the x values that I'm getting. The other x value that you can get from over here, if again I do calc 0, go all the way to the right, and then make sure my left bound and right bound is correct. All right, so there's good enough. That's my other x value. So 93.35. You think in terms of significant figures, I'll just show you quick. 93.35. If you think in terms of significant figures, it would be 1, 2, 3. Round it up or keep it the same. You round it up. So significant figures here would be 9.34. Sorry, 93. I'm trolling. 93.34. Ah, I can't math. 93.4. All right, awesome. So these are the two values of x that you get from here, right? So that's one way to solve it. Of course, you could have used quadratic formula and a bunch of different stuff. The other way to solve it, in case it's easier for you, I'd rather show you, is using the calc intersect trick. If you're good enough with this explanation, you can probably skip ahead in the video, but I will show you one more tool. So your other tool is calling this, let me use another color, is calling this y1 and then calling this y2. And so if you call that y1, so 800 will be y1, and the y2 will be this guy here, the 1212 minus 4x minus 3600 divided by x. If you go ahead and graph this, well, then I can change the window immediately because I sort of know the answer already. I know that x ends up being those values here. I know that one of my y's is 800, so I'm going to put a y max of 900. If you go ahead and graph from here, you're going to get two intersects. Now notice, why do I care about intersects here? Because these two equations, the y1 and the y2, what are they doing to each other? They are equaling each other. So wherever two lines are equal is where they intersect. So, the other trick is using calc intersect. If you use calc intersect here and call this y1 and call this y2, you can go second, trace, enter to hit calc, go to intersect instead, pick your first curve, make sure it's your first curve because sometimes people press down or upwards and they skip, ¿cierto? I mean, they jump from one to the other. So your first curve is going to be the flat one. The second curve is going to be the red one. Go ahead and press guess nearest to the first one you want. And there you go. You got the same answer, the 93.35, which we left as 93.4. And for the other x value, again, you press the blue one as the first, or the flat one as the first, and then the red line as the second, ¿cierto? And then the guess near the one we want now, 9.64. So both solutions work. Do whichever one is easier for you to understand. Okay, for me, I love the calc intersect trick, but I know that is not everyone's bread. Okay, so to each their own. Whatever floats your boat, here are the values for x. Now we're not exactly done yet because here it did say, and never forget, to find the possible dimensions of the park if the area of the garden is 800. So you got two values for x. ¿Cierto? You got a 9.64 and a 93.4. And so technically, my only condition for x is that it has to be between 3 and 300. Both of them fulfill that. So this is a little bit more of an annoying sort of exercise, but I guess what we should be answering here are the two different lengths and the two different widths we can get. So on the one hand, using light green, so light green for this scenario, okay? So on the one hand, you can have a length of 9.64 and a width, this is in meters, right? Yeah. So on the one hand, you can have the scenario of 9.64 meters for length and the width of 1,200 divided by 9.64. And the width of significant figures, you can leave it as 124. Yeah. 124 meters. So that's the first scenario, ¿cierto? A length of 9.64, a width of 124, or the scenario in dark green, which is with the other value of x. The scenario in dark green would be the length of 93.4 meters and the width of 1,200 divided by 93.4, which would give you a width of 12.84. And in terms of significant figures, it's 12.8 meters. So these are your two scenarios for length and width. You either have a length of 93.4 with a width of 12.8, or, let me leave clear that this is a decimal, see, 12.8. Or you end up with a scenario of 9.64 length and 124 width. If we check the answers over here, you can see of both scenarios, right? So on the one hand, you have the 9.64 or the 93.4. And so one of the scenarios for width is 124 or the 12.9, ¿cierto? So as long as you express both scenarios, you're gonna be good to go. I know here I put 12.8. That's only because I was using significant figures. As long as you're consistent in your procedure, you're still gonna get full points, ¿cierto? In fact, here it says accept 12.8 for the second value, right? That's because you're using 3 significant values. So as long as you're consistent with the significant values in your procedure, everything will be okay. So trust me on that, all good, no worries. Yeah. And then we have the hard parts for part C. Maybe even why you clicked on this video. So for part C, we need to find an expression for that. What the heck even is that? See, this, you guys, is the derivative of a in respect to x. So you take this equation here and you will do the derivative in respect to x. There's 2 main things I have to go over. The first one is derivatives, of course. But the second thing I have to go over is that, notice, for part C, you need nothing from part B and even nothing from part A. Because this because this show that is telling you that this information is true. It's like, I don't know, show me that the earth is round or something like that. See? We know that it's round, you just have to prove it. So you can, in other experiments, use the fact that the earth is round to your advantage. This is the same scenario. For part C, you need to do the derivative of a in respect to x. Well, you already have the derivative. You already have function a in terms of x. So you can actually already do it because you know that this information is true. Why do I mention this? If the day of the test you are running low on time and you need to claw for points, search for phrases that say show that. Because that might allow you to skip ahead and do something like part C. I'm just saying, that's the kind of stuff that might give you the extra edge you need the day of the test. Anyways, from here, we simply need to do the derivative of that equation. ¿Cierto? So that equation is, a equals 1212 minus 4x minus 3600 divided by x. Dale? Now, if I go ahead and open up the formula booklet and I look up derivative, here it is. ¿Cierto? So the derivative of an exponent is the classic. For me, it's much more well understood if I just give examples. So for example, if you have x squared, the derivative of this is 2x. If you have x cubed, the derivative of this is 3x squared. This is consistent with the formula. Notice, focus on the n. What is happening to the exponent? On the one hand, it's going to go down in front, multiplying. And on the other hand, it's going to get a -1 up top. So for example, the in-between step that's happening here is that you end up with, well, this is going to go in front, it's going to be 2x. And on the exponent, you do 2 minus 1. And so 2 minus 1 means you end up with a 1 on the exponent. Dale? The in-between step over here is that this 3 goes down in front multiplying, so you end up with 3x to the power of 3 minus 1. 3 minus 1 is 2. There you go. All right, that's the in-between step. It's all that's really happening. It's 2 things. The exponent multiplies in front, and the exponent gets a -1. Now, the interesting scenario, which is what they throw us immediately, is when the x is below, ¿cierto? So when the x is in the denominator, how does this work as an exponent? Guys, that's the other thing I have to explain very quickly. Technically, I guess I'm going to... it's a classic, I always show it. You can skip ahead if you already know, but basically 2 squared is 2 times 2, which is 4. 2 to the power of 1 is 2, which is 2, and 2 to the power of 0 is 1. And 2 to the power of -1 is 1 over 2, and 2 to the power of -2 is 1 over 2 times 2, in other words, 1 over 4. So notice, there's a certain pattern here that is clearly arising. When you want to go up, all you have to do is multiply by 2. And when you want to go down, all you have to do is divide by 2. And so there's two main things that we're learning here. On the one hand, when you have a negative exponent, ¿cierto? It means that you sort of have to like flip it. Okay, that's what I need you to get into your brain. If you have, for example, 2 to the power of negative 2, first you flip it, and then you do the exponent. That is what I mean by flip it. Okay? So that's one thing we can learn from this example I just gave. And the other thing you can learn is that notice, this 4, when you divide by 2, you go from 2 squared to 2 to the power of 1, ¿cierto? And this 2 to the power of 1, if you divide it again, you end up with 2 to the power of 0. And here you're doing 2 divided by 2 equaling 1. And that is why, with what I'm putting in pink here, this 2 divided by 2 equals 1. That is why anything to the power of 0 has to equal 1, because eventually you will do itself divided by itself, and itself divided by itself has to equal 1. This is a pattern that happens everywhere. 3 cubed is 27, 3 squared is 9, 3 to the power of 1 is 3, and eventually you face the same problem or the same pattern, ¿cierto? Here you divide by 3, here you divide by 3, 3 divided by 3 equals 1. So, two main things we learned. Anything to the power of 0 has to equal 1, and for negative exponents, you will be flipping it as shown right here, ¿cierto? Now, this also applies in the other direction, okay? What do I mean by this? Before doing the derivative, make sure you get the exponent in the denominator out of there, ¿cierto? So because a negative exponent means that you flip it, well, if you want to flip it from here, you can actually go the other way. So flipping it from here means you end up with x to the power of negative 1. Because x, and this is the big brain play, see? X to the power of negative 1 is 1 over x. X to the power of negative 2 is 1 over x squared. Ah, that makes a little bit more sense, doesn't it? And so right now, we just had a 1 over x. We want to be able to see the exponent so that we can do the derivative of an exponent more easily, ¿cierto? For the derivative of an exponent, it's easier if it's up top. So this is what we're applying right now, ¿cierto? You want to get rid of the x in the denominator. You want to put it up top. But because it's in the denominator and you're flipping it, the moment you flip it, you're putting a negative exponent. So this is the equation for area simply rewritten. Okay, all you really switched around was this guy here converted to this guy here. That's all you did. Everything else is the same. And from here, we can do the derivative of an exponent. So from here you do the derivative, and from here you realize, well, this 1212 doesn't have an x, so this 1212, boom, disappears. This minus 4x, you have an x to the power of 1, so this is going to be 1 times negative 4. So minus 4 times 1 times x to the power of 1 minus 1, ¿cierto? Following the rule of, first of all, the exponent multiplies in front, and second of all, you do a minus 1 to the exponent. Minus 3,600 times negative 1, because it's this exponent here, ¿cierto? Going in front, times x to the power of negative 1 minus 1. And so from here, what you end up with, clearly, this ends up as x to the power of 0, and anything to the power of 0 equals 1. We learned that a second ago, so you end up with minus 4. Here you have a negative times a negative, so it actually ends up as plus 3,600 times x to the power of negative 2. So if you were to rewrite this and leave it a little more pretty, if you'd like to, you can leave it as 3,600 divided by x squared minus 4. That would be for part C. Just so that you all believe me, there it is. All right. And so for part D, it literally says use your answer from part C. okay, to find the value of x that will maximize the area of the garden. Now, so here, there's a quick sort of hint that I have to give you, okay? Guys, whenever you want to maximize or minimize something, or even more generalized, whenever you want to optimize something, you have to ask ChatGPT. Nah, just kidding. Although that is kind of true. Whenever you want to optimize something in math, and when I say optimize, I mean that you either, for example, maximize, I don't know, benefits, maximize area, or minimize costs. All you have to do is take your derivative and equal it to 0. And I'm going to have a quick 1 or 2 minute explanation of why you have your derivative equal to 0. But for now, you can go ahead and jump to the solution, which is, okay, so that means my derivative has to equal 0. That means I need to find 0 equals 3,600 divided by x squared minus 4. So you can go ahead and start solving for now. I will explain, however, why you have your derivative equal to 0, because oftentimes I see that people don't know, and you're here to learn, right? You're here to learn, I suppose. So the explanation that is probably not going to be that quick, but I'm going to try, is the following. Let's say you have a parabola, see? So a function that looks a little bit like this. The thing I'm putting in red right here. Okay? In its original version, let's say it's x squared plus, I don't know, 3x plus 2. I'm just making it up. I don't think it actually looks like this. I'm just making it up on the spot. Not it? If you have something that looks like this, if you were to plug in an x, you would get a y. For example, if you plug in an x of 0, boom, boom, you end up with a y of 2. If you plug in an x of 1, you end up with 1 plus 3 plus 2, you end up with 6. ¿Cierto? And so if this is the main idea, in the original, right? So in the original, if you haven't done the derivative, if you haven't done the integral, if you haven't done anything at all, this that you're getting right here are sets of points. Whoops. Yeah, it's 0, 2. It's 1, 6. They're all like x, y coordinates. Yeah. The main idea is that when you do the derivative, which if I were to do it right now, you end up with 2x plus 3. Okay? When you have the derivative, it's not exactly sets of points anymore. ¿Vale? I mean, this x is giving you an x coordinate and the y coordinate that you graph onto your graph, of course. But now, what you're asking is a little bit different. See, for example, if you plug in an x of 0 here, your y ends up as 3. If you plug in an x of 1, your y ends up as 5. And this is actually a little bit different, see? Because although you can also say that, oh, okay, this is also like an xy coordinate, ¿cierto? This is also like, I just found the point 0,3, I just found the point 1,5, but the context is different because the context is that of a derivative. The main idea is that in the original, basically you are asking your function, when x is this, what is my y at that point? Instead, in the derivative version, you're saying, when x is this, what is not your y, what is my slope? When you do the derivative, it actually helps you find the slope. So in the original, when x is 0, y is 2. When x is 1, y is 6. In the derivative version, when x is 0, my slope is 3. When x is 1, my slope is 5. So, that makes a little bit more sense. And actually, if I were to graph this very quickly, just so that we're all on the same page, I think it's important for us to understand this explanation, because I wish someone told it to me back in my day, but, well, at least I'm here to tell you now. We go ahead and do maybe zoom standard would be fine. So notice, you end up with something that looks a little bit like this. Okay, so what you discovered from the original, which I'm putting now in red, so from the original, you discovered that when x is 0, y is 2. You discovered that when x is 1, y is 6. So you ended up with something that looks a little bit like that, ¿cierto? But in pink, the derivative, it's basically, when x is 0, the slope is 3. When x is 1, the slope is even greater, the slope is 5. So notice, it's a little bit different, the information it's giving you. Now, following the idea of the slopes, because I did say you have to have your derivative equal to 0, ¿cierto? Now, why do you have your derivative equal to 0? Because, well, if your derivative equals to 0, I'm saying that your slope is 0, ¿cierto? So basically, you're working backwards. You're saying, okay, if my slope is 0, what is my x? That's what you're saying. So if your slope is 0, well, where is your slope 0 in a parabola? Over here, you have a slope of 5, because you discovered it there. Over here, you have a slope of 3, because you discovered it there. And if you keep going, here is like a slope of 1. And here, ladies and gentlemen, you have a slope of, there is your slope of 0. And so if you plug this into your derivative function, you're saying, when my slope is 0, what is my x? And even in this same example, when my slope, so this entire thing, ¿cierto? This is y. When my slope is 0, what is x? So 0 equals 2x plus 3. That means that 2x equals negative 3. X equals negative 3 divided by 2. So that means that at this point here, you have negative 3 divided by 2 for x, ¿cierto? So x equals negative 3 divided by 2 right at that minimum point. See? And so, notice, the main idea, or what's happening here, is that at the min or max, your slope is 0. And so if you take the derivative and you equal it to 0, you will successfully be asking your derivative function, yo, when my slope is 0, what is my x? And you know that when your slope is 0, you will be at the minimum or maximum. And so what you know of the minimum or maximum right now is that it lies at negative 3 divided by 2. All right, so if I apply that down here, it's the same idea, okay? So you took your derivative, you equaled it to 0 in order to find the value of x. You're also finding the value of x up here. You discovered it was negative 3 divided by 2. You will be doing the same thing down there, ¿cierto? So from here, you need to get x alone. There's a couple different ways. You can use y1, y2. It's a trick that works. For me, I see a relatively more cool way to solve it. And the cooler way is that, yo, you have an exponent in the denominator. Nobody likes that. Multiply everything by x squared. So if you multiply everything by x squared, this goes away with this. And you will end up with, well, 0 times x squared is still 0. 3,600 remains by itself. And the 4 is multiplied by x squared. So from here, get x alone. So you can do plus 4x squared, plus 4x squared. So 4x squared equals 3,600. You can divide both sides by 4 in order to get x alone. So x squared has to equal, I think that's 900. Yep, it's 900. And from here, you gotta do square root to both sides in order to have this go away with this. So x has to equal plus or minus, because it is square root, plus or minus square root of 900. 30. Sorry, plus or minus 30 like this. See? In case you're confused by the plus or minus, yet another quick explanation, is that when you find the square root of something, so you're basically asking, in terms of math, which number multiplied by itself gives me what's inside. Which number multiplied by itself gives me what's inside. So you can do 30 times 30 gives you that 900, but you can also do negative 30 times negative 30. And that also gives you 900. So that is why for solutions with square root with a base of 2, you always leave your answer as plus or minus 30. However, in this context, ta-da! I told you it was going to be relevant. X has to be between 3 and 300. So between X being negative 30 and X being 30, clearly you end up with the choice of X being equal to 30. So here we can change the plus or minus to simply be X equaling 30. So that would be for part D. And last but not least, we need to find the maximum possible area of the garden. Well, we know that at X equals 30, we have our optimal point, therefore for maximizing the area. Now we have to find the actual area. And so the area formula is right here. It's the one we've been using all along. So all you have to do is plug in 30 into that. So you do 1212 times 4 times 30. Oh, I just rolled. 1212 minus 4 times X, which we will be calling 30, minus 3,600. You put the fraction using alpha y equals, then pressing the first. 3,600 divided by 30. You check your work. It's asking for area of garden. This is for the area of the garden. That should be fine. So I'm going to go ahead and press enter. Just checking one more time. It's good habit. You press enter, 972. So for part E, all you did was plug in 30 into your equation for area. So you ended up plugging in 1212 minus 4 times 30 minus 3,600 divided by 30. All right, did run a little bit out of space near the end, but hey, that was an intense problem. I think we earned it. See? So don't forget your units, meters squared. I show you the answer key so that you keep believing me, even though I always put it at the end. Here you have the X equals 30, and here you have the 972 meters squared. Ladies and gentlemen, number 5 was pretty intense. Number 5 was pretty intense, but I think we had a pretty good explanation of how derivatives worked. We learned more than one thing today, and that's the idea. I hope it helped. That is for number 5, and that is for the entire paper. See you around.